but life pulled us apart, left me talking to the dark. If I called you tonight, would it feel the same? Or have we both moved on to different names? Take me back to the start, before the quiet and the scars, when the world felt small and your hands felt warm. Take me back to the start, if only for a moment. I've been up since 3, scrolling back what we...
Oh my gosh, I completely flopped tonight. I don't know what the hell was going on. Yeah, all sorts of technical issues. Okay, you're entering into the end just before the exams. Right, let's go. Let's give you a few warm-up questions. So have a go at these ones. Use the correct letter V, W, X, Y, or Z to answer each question. Which element is a transition metal? Which element is in group 2? Which is a noble gas? Which element has a proton number of 4? And which element forms only 1 plus ions? Oh. Cool. Let's move on, because what's going on? This hasn't got no charge either. What is this going on? It's all going a bit Pete-tong. Hello, hello, hello. Yeah, don't worry, I've had a mare today. I've had a complete and utter mare. So, yeah, all going a bit pear-shaped. All right, let's go. Let's get into things. So, I'm gonna speed through some things for you. So, and then you can put suggestions up of what you want me to go through. Oh my days, what's going on here, Bob? Right. Don't forget, this is how to calculate the relative atomic mass. So for those of you that don't, watch out. Make sure you do the mass number times the percentage abundance over 100%. So for example, here we would go 20 times 90.48. This is if you're asked to calculate the RAM, the relative atomic mass. And then you would add all of these up. So you do 20... you'd add that to 21 times 0.27, and then you'd add that to 22 times 9.25. Smash that all in your calculator, and you would divide that by 100%, and that would give you the RAM. Don't forget RTFQ, read that beep question, because 3 significant figures. So we smash that all in the calculator, and then I'll go over one to watch out for, because they do try to trick people on this. This is quite standard and easy for most people to do. He says, oh my gosh. So there's a good chance you get this tomorrow. One like this, as it's come up very, very regularly. And I got 2018.77. I'm going to divide by 100 and see if I've made a mistake. I got 20.1877. So if you smash all of that, if you sum all of that and then divide by 100, I got 20.1877. Now, 3 sig fig. What we saying, peeps? Is that 20.2? Or is that 20.20 or 20.19? What is that as 3 significant figures? Help me out, people. Is that 20.2? So, if we look over here, when you're doing this, what you want to do is make sure you do the mental maths and say, right, 90 times, there's more 20s, so it should be closer to 20. So you smash that all in, and then you're like, yeah, my answer is quite close to 20, so that sounds about right. Now, the other thing is, watch out if they're sneaky. You always times the mass number by the percentage abundance. So make sure you do this. Oh my days. Make sure if you have like one which says carbon 12 and carbon 13 and that, and it says that, you get a table like this, and it has isotope, and then it says like, I don't know, I'm making this nice and easy. That's 2% and that's 98%. Work out the RAM. Some of you might get messed up because they've put the atomic number in there. They've done that to mess with your head. You're looking at the mass number. It's the mass number times the percentage, not the atomic number. So it's always the mass number times the percentage. You'd sum that. So for this one I've done there, you go 12 times 2 plus 13 times 98. That's not the real thing because it'd actually be the other way around. It'd be like 98 times 12 in real life, but I just made that up off the top of my head. And then when you divide that by 100, you'd find that that is very close to 13. So that'd be like 12.9 or whatever. Okay, cool. Everyone cool with RAM? Is everyone good with RAM? Hopefully, you're all cool with that. Just going to rinse through a few more things from Unit 1. So don't forget, if we want to separate an insoluble solid from a liquid, we are going like sand and water. You're just going to use filtration. Don't forget the names of the stuff. You've got filter paper, clamp and stand, and you've got a beaker. Easy peasy, pudding and pie. This does come up in the Making Salt Practical, which I'll go through. This is distillation. I know, AI made that for me. Look how stupid this is. Why has it got steam coming out the top? Anyway, forget the steam coming out the top. That's just that AI business going on there. Right, so what we got distillation going on here. If you get a question on distillation, you're looking at two key things happening. You're looking at evaporation. That's going to be a key word as to what happens in distillation. So essentially you have a heat source causing evaporation, and then this is known as a condenser, if my pen will work for me. And 10 points if you can work out what a condenser does. It does condensation. So the moment they say distillation and you're talking about that, normally on the mark scheme, the word evaporation is going to appear in condensation if you have to explain how it works. So you're going to heat something to its boiling point, and that is going to evaporate and then condense in the condenser, which is kept cold, and it will condense and come off and separate. Now, fractional distillation is when you have two or more liquids together and they all have different boiling points. You can hold the heat at the lowest boiling point and bring that off first. So if you have like, if substance X boils at 70 degrees, then you hold the heat at 70 until you don't get any more drips coming out. Then you know I've boiled, I've evaporated and condensed all of substance X. So in a mixture, this is separating mixtures. If you have substance Y and that boils at 80 degrees, we don't want it to go to 80. We want to keep that in there, and we're going to get X in here and we're going to leave Y behind there. But let's pretend we've got three substances. What do you do then? So if I have substance Z, which boils at 90, I'm going to hold it at 70, and then I'm going to replace this with another one. So I boil at 70 until all of that's come off. Once it stops dripping in there, I know it stops condensing. I know I've got all of substance X off. I then hold it at 80 and off will come substance Y, and then I could heat it to 90 to get rid of that, or you just have your substance Z would be left in there. So that's how you can do separation. Now you would need a thermometer for that, and that would be called fractional distillation. So when you have a mixture of liquids, it's called fractional distillation, and you use a thermometer and you hold each substance at a different temperature. Okay, let's zing zang on. I'm just gonna whiz through the content today because I'm going a lot quicker today. So what is this a picture of? This is some salt crystals in a dish by the window because we're doing crystallization. You want it in a cool, dry place. Now, crystallization here, folks. What we're going to do with crystallization is, if you had a solution, right, of sodium chloride, and the question said something like, how would you get dry, pure crystals of NaCl. Okay, so how am I going to get sodium chloride as a solid out of this? This might be worth 2 marks or 3 marks maximum. And this isn't how they normally ask it. Normally crystallization comes up with salts, but it could come up separate. It has come up before in chemistry for AQA separately as well, like this. So what we would do here, they could say magnesium sulfate. They could give you any type of salt. They could give you copper sulfate, which is blue. How would we do this? What we would say is gently heat. And you can put it in the chat if you think you know. So you would gently heat. Evaporate is the key word again, just like in distillation. But we're not doing condensation here. So evaporate water. We're not evaporating all the water, just some of the water until crystals appear. And then what we want to say is leave in a cool, dry place. Oh my days, have I run out of room? I probably have, haven't I? Yeah, I have run out of room. Leave in a cool, dry place for crystallization to occur, and then dry with a paper towel, and that would get you all of the marks. Okay, so just remember that, and we're gonna come back to that in a second. When we go through making salts later on, we'll go through that core practical. But I know what some people say, sir, this is paper 2. Guess what? Chromatography can come up in a small question in paper 1 because it's part of unit 1, separating mixtures. So just remember all your bits and pieces. You got filter paper, optional. You can call this filter paper. You can call this chromatography paper. It's up to you, whatever you prefer. Chromatography paper. Now, what you're going to do, you're going to use a pencil line for this. If they ask you why do you use pencil, pencil is insoluble in water. So when we use water or ethanol, pencil won't dissolve. So either alcohol or even propanone, like nail varnish remover, it won't dissolve. So pencil's generally pretty insoluble, graphite, in most substances. So pencil's insoluble, it will not run. Now, I don't mean like run, by the way, is the word in the English language. It's got 14 different meanings. Going to run to your exam tomorrow. Don't let the ink run. You're going to run out of time. Anyway, enough of my rubbish. Don't run your mouth. Right, here we go. What we got, the solvent has got to be below the pencil line. Just remember that, solvent below pencil line. Okay, what else? If a colour stays on the line like that, folks, if a colour stays on the line, it's insoluble in that solvent. But I could use a different solvent and make that colour move. So this is insoluble. It's not moved off the line. So that's insoluble. The most soluble is the one that's moved the furthest. So this would be most soluble. It's moved the furthest. And the least soluble is that blue one, but the totally insoluble is that red one. I guess that's the least soluble, the red one there. And then the blue one there is not very soluble. And then you need to know how to calculate the RF value. Hopefully you all know that. You take your paper out before it reaches the top and you draw a line called the solvent front. And you divide the distance that your particular color you're looking at has moved. So like if the orange moved 0.6 and the whole solvent, the water in my beaker, moved 2 centimeters and this moved 0.6 centimeters, I would go to, it wouldn't do that, would it? That's a bit, yeah, it might do. That looks over halfway, so I should probably say 1.5 centimeters. So if you wanted to calculate the RF, it's a fraction, a decimal. You're going to do 1.5 over 2, and you get like 0.75 would be your RF value. You can then say, look up in a book and identify the substance. Anywho's, let's move on because we don't want to waste time, too much time. Here we go. Let's do this question that will just test you a little bit on that. Which apparatus could be used to collect water from the sodium chloride solution? Which apparatus shows filtration? Oh yeah, the grid box podcast. Yes, you can talk about attraction, affinity or attraction to the water, the mobile phase or the stationary phase. I mean, generally that comes up in paper 2, but you can talk about that as well. So you can talk about the one that has moved the furthest has a greater affinity in the mobile phase, the solvent, a lower affinity to the stationary phase, the chromatography paper, or filter paper is easier to say. Or you can bus out the one that has moved the furthest, has the least affinity for the paper, which is the stationary phase because it doesn't move, and a higher affinity or attraction to the mobile phase. Affinity, attraction, same thing. Okay, let's move on. Hopefully you know this. If you want to collect the water from the sodium chloride solution, we're going to use distillation. You're not going to collect water with this crystallization here. The water's going to escape and go off. So you won't be collecting any water with D. So you want B for that. And then A is filtration. And if they had an option, how would you separate pigments or colors? That would be C, which is chromatography. Let's zing on. I don't want to take too long, peeps. Okay, this is just a reminder for me. I want to talk you through quickly the development of the atom. So chemistry A level or biology A level's harder? Well, biology A level is, let's have a little think. Biology A level, the conceptual stuff is easier to the majority of people find biology A levels concepts easier, but chemistry's concepts, conceptually, it has some skills that are very difficult, and if you're mathematically brained, those skills are easier for you. So chemistry has a whole chunk of it that is not down to maths, but it has a big chunk of it that is down to your mathematical brain for solving problems. Are you good at solving maths problems? Like when you do GCSE, when you're like solving these maths problems in chemistry, A level takes that a step further. So there's really difficult maths problems you've got to solve. And if you're good at that, titrations and rearranging calculations, then that's right up your street. However, if you're asking me which is better to take for A level, it's kind of like horses for courses. Biology has a 10% lower grade boundary, so across all exam boards, about 70% gets you an A star in biology A level. Generally, 70% will guarantee the A star. Chemistry can go from 80 to 85% to get an A star at A level. You might say, why? Chemistry's harder. How can a grade boundary be 15% or 10% more? Because think of the type of kids in your year that take chemistry. Who's going to take chemistry and who's going to take biology? Enough people are going to go, I think I like psychology, bit of philosophy or music, art, and I'll stick biology in there. They're not so mathematically brain-minded, and that the grades for the A-level biology can be a bit lower. And biology also, as you'll probably see from B1, is very tricky, and they ask you lots of questions that you haven't revised, whereas chemistry is a lot more straightforward, like maths GCSE. Did you practice this skill? Can you apply this skill? And that is more like chemistry up your street. Yeah, but most of the people that take chemistry A-level are going to be people that are also taking physics and maths. So you're up against that top percentile of people in the country. Remember, the boundary is set by everyone taking it in the country. So if you dare to take physics or chemistry or maths, the grade boundary in maths A level is very, very high to get an A star. You probably need like 85% to 90% to get an A star in A level maths or something crazy like that, because who's taking A level maths? It's all the super smart kids. And that sounds really bad to say that, but I mean the super smart as in their brain works in that way. Whereas biology has a much wider range of students taking it. You've got students who are more art inclined, or myself, I did English literature and I did biology. So, I probably brought the grade boundary down for biology. Yeah, right. Let me go through the... so yeah, I mean, biology's easier to me, but... Right, chemistry. Here we go. What are we going to do? We're going to say the development of the atom. So along came a guy called Dalton. Dalton believed that atoms were solid balls. And then along came J.J. Thomson, who discovered the electron. The electron was discovered first. And J.J. Thomson came up with the plum pudding. Make sure you know how to describe the plum pudding. If I said to you, how do you describe the plum pudding model? What would you say? Because that has come up several times for like... 2 marks. What is the plum pudding model? And you should be able to say it's a sphere or ball of positive charge with electrons embedded throughout. If you can't come up with them fancy words, you're not going to gain marks for fancy words. If you just say it's a ball of positive charge and there are electrons in it that can't move, stationary electrons stuck inside it, you get the marks. You just have to describe it. So that's the plum pudding. And that was... J.J. Thomson discovered the electron, and the plum pudding is part of that discovery of the electron. Now, next we have the discovery of the nucleus. And how was the nucleus discovered? So the discovery of the nucleus was by Rutherford, and he did the gold leaf practical. And what Rutherford did, bosh, I'm just going to go through this nice and quick, and then we're going to do questions. But I'm going to smash through as quick as I can. Unit 1, we'll do some questions. It'll take about 35 minutes maximum, and then we're going to do some questions. So we're going to smash through today a lot faster. So there we go. Here's the plum pudding. How did they disprove this plum pudding? Well, Rutherford fired alpha particles at it. He thought they would all go through. He said, yeah, man, they're all going to go through. That's what he believed, because he believed in the plum pudding. But like a good scientist, he wanted to review other scientists' work. And that's what good science does. It checks each other's work out. And they say you should be happy when someone proves you wrong, your theory wrong, because it means that science has moved forward, and you were part of that by making a theory that ended up being incorrect. Anywho, what did they find? Well, what the actual findings, I'm going to draw in orange, instead of them all going through, what they found is that 99% went through, most went through, and this proved, if you get a 6 marker on this, atoms are empty space, mainly. I should have said atoms are mainly empty space. That's what it proved. Some particles came right back, and this meant some alpha particles bounced straight back. Some hit a dense nucleus, and then some curved away and were repelled. Remember, alpha particles themselves are positive, and so they were repelled by the positive nucleus. And this proved the nucleus is positive. So some deflected. When I'm saying some, I'm talking about these alpha particles. They deflected, proving nucleus was positive. We're going to do questions, so I'm not going to get too deep on it all. Is everyone cool with that? Yeah, some bounce off, some deflected, some span off. You get the idea. All right. Everyone's cool with that. Now, there then came a dude after this, and this dude was... so, from this, they kind of thought the atom looked like this. Rutherford's model was like this. Positive nucleus. I should really do like that. Positive nucleus with electrons whizzing around like this. Of course, this model was changed, and a guy called Niels Bohr, he's the guy that told us about the 288, right? So he was the one who said electrons orbit the nucleus in shells. He did a bunch of math calculations to do that. And finally, a guy called James Chadwick discovered the neutron. Bish, bash, bosh. What do we want to do? We want to move on, is what we want to do. Okay. Hey, some of you guys need to know about transition metals. So let me rinse through some knowledge on transition metals for you. If you're doing triple science, you need to know about transition metals. This will only take a minute in unit 1. So transition metals, aluminium is not a transition metal, but copper is a transition metal, and they're found in that middle block. They don't have a groove. Platinum's used as catalyst, copper sulfate has color, nickel's a good catalyst, and iron bridges. So transition metals, uses, you need to know uses of transition metals. And this is if you're triple. So if you're triple, you need to know they have high MPT, melting point, which is great because your bridge, you don't want your bridge to melt. They're strong, they're solid, they're hard, strong, solid, good conductors. What of heat and electricity, which is why copper is great in wires and in cooking utensils. Good conductors of heat and electricity. What else can we say about transition metals? They make good catalysts. Catalysts, if you're asked, speed up reactions without getting used up. So iron in the Haber process, you have platinum catalysts used in all sorts of reactions, nickel catalysts used in loads of reactions. Like hydrogenation and stuff like that. Right, good catalysts they make, and they form coloured compounds. So anything with a colour in it, and this goes into your paper too, when you think about the tests for cations and the iron 2 Fe2 plus ions with hydroxide, sodium hydroxide, form a green precipitate. Fe3 form a brown precipitate. Copper forms a what? Copper forms a blue precipitate. So transition metals form colored compounds. Aluminium, white. Calcium, white with sodium hydroxide. Magnesium, white. In fact, all group 1, 2 and 3 compounds are white only. So there is no such thing as a colored group 1, 2 or 3 compound. They're all white. Yeah, and the last thing, they have multiple charges. So like iron can be Fe2 plus or Fe3 plus. Okay, cool. Yeah, ductile, malleable. Yeah, you're right, Cheese 30379. He said Bohr said that they orbit at specific distances from the nucleus. Yes. Excellente. Coloured compounds, brilliant. Yeah, I will go through bonding. Okay, see if you can do these two on transition metals. 3 ticks. Which is the most likely metal in a blah blah catalyst? All they're asking you to do here is realize, oh my gosh, come on. Catalysts are transition metals. If you're a triple student, you need to know that. And so aluminium, that's in group 3. Barium, I think that's group 2. Potassium, that's group 1. Vanadium is going to be our answer here, and the reason, because vanadium is in the middle block of the periodic table. Now, which two are typical properties? They can be bent and shaped. Someone in the comments said that awesome word, malleable, and yeah, they can be bent and shaped. That's why we can make our cars from steel, like transition metal. Steel contains iron. Steel is an alloy. But good conductors of electricity. Yes, the top two. They don't have a low density. Alkali metals do. Group 1 and group 2. Yeah, low melting point, no. Group 1 do. And poor conductor of heat, no. They're good conductors of heat, hence why we make copper frying pans and steel frying pans, which contain iron. Right, I am going to go through everything, but I'm just whizzing through. Don't forget about Mendeleev, peeps. So what did Mendeleev do? Mendeleev is the dude that developed the periodic table. Now, when he developed the periodic table, remember how he arranged it. How did he arrange the table? Does anybody know how he arranged the table? He arranged it like everyone else. He arranged it by atomic weight. We don't do that now. That's not the modern table. So the old table was arranged. I'll give you the bullet points. Okay, I'm just going to give you the bullet points. Oh my days. He did a couple of funky things, but the first one isn't really funky. Arranged by atomic mass or weight. They might use the word weight, or they might say mass, but arranged by atomic weight. But then, of course, he prioritized. Do you know what? You don't need to say he prioritized. You can just say he moved them about so they fit with their chemical properties. He prioritized chemical properties. What I mean by that is, even if he lined them up in order of weight, if he found one was more similar to another in terms of they both bubble in water, he was like, ooh, I'm putting them in the same group. So he moved stuff about, and then finally he left gaps. Okay, so he left gaps. Why did he leave the gaps? He left the gaps and he said, look, I reckon we will discover an element in the future that will fit there. And later on, scientists discovered elements that fit there. And so that worked. Okay. Right, so arranged by atomic weight, prioritized chemical properties, and he left gaps. Boom. So two of the most famous ones that he switched, so they're probably used in your exam, is tellurium and iodine. Now, originally, you can see here, iodine, tellurium is heavier than iodine. So originally, iodine, came first, and then tellurium. And so the original position, and then he switched them up. He switched them up, and like now they don't. Tellurium came first, sorry, then iodine, and then he switched them up. Whatever. He mixed them around and basically put them in a different order. And the reason is because he found that iodine was more similar to the other halogens. So he was like, no, I'm putting iodine there and tellurium's getting moved. Anyway, he switched them based on their chemical properties. And so their weight is slightly different. Okay, have a go at these questions. And then we're going to move on. Need to go fast. He left, you're right there, someone in the comments said he left gaps for undiscovered elements. Absolutely. And later on they were discovered by other scientists. So this meant that it gave evidence to prove him right. So yeah. What are the columns known in the periodic table? Oh my gosh, that's easy peasy pudding and pie. The columns are known as groups. And the elements are arranged in order of, this is in your periodic table. They're arranged in order of atomic number, so that is different. This is the modern one, is not by weight. Modern table, the one you use, is arranged by atomic number. So just remember that. That's how the main changes. What else? See if you can do these three. What are the three words? So Mendeleev first arranged the elements in order. How did he first arrange them? And all scientists did this. He did it by atomic weight. Give yourself a pat on the back if you got it right. And then, oh my days, my phone ain't stopped buzzing. Right, Mendeleev then placed the elements with similar properties in columns called groups. And when the next element did not fit the pattern, did he ignore it, leave a gap, put the element at the end of the row? No, he left a gap. So he left gaps. It was arranged by weights. Blah, 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 blah. You get the idea. Right, let's look at alkali metals. We're near the end of Unit 1. There's 4 units to go through. So spot the AI mistakes. Oh my days. Alkali metals. Look, alkali metals are like lithium, sodium and potassium. And they're light, so they float. So alkali metals have low density. So often you can describe them floating. You do need to know the reaction of the alkali metals with water. Oh my gosh, they said that's an albecky pop. Have you ever heard AI might conquer the world, but it's not ready yet. It couldn't come up with a squeaky pop test, so it called it albecky pop. I don't know what that is, albecky pop. And yeah, that's supposed to be a pH scale showing that it's alkaline. Yeah. And look, have you ever heard of an alkali metal called squeezium? Cesium, I think they were trying for there. Here's the old squeaky pop test. Why am I talking about squeaky pop test? Let me get on and show you what you need to know and then give you some questions. I'm going to go straight into the questions. In fact, I'm just going to talk about it. So, alkali metals, they have low density. They're soft, easy to cut. They float. They're very reactive because they have one electron in the outer shell they want to give away. As you go down the group, the electron is further from the nucleus, so it's more easy to remove because it feels the attraction less. Also, there are more shells as you go down the group, down the periods in the group. You're going to increase the number of rings or shells of electrons. This increases shielding. You can use that term at GCSE and you'll get a mark. So you'll often get a 4 marker. Why is potassium more reactive than lithium? Well, as you go down the group from lithium to potassium, you get more shells, so more shielding. The electron is further from the nucleus, so feels less attraction, and therefore it requires less energy to remove that electron. And alkali metals are trying to give away an electron when they react. So the ones down the group react the most violently. Lithium fizzes around and bubbles around on the surface of water. Sodium burns with a yellow flame, like my incredible picture here, and potassium burns with a lilac, pink or purple flame. You'll get the mark for any of those. What is it that's burning? Well, it's the hydrogen gas that comes off. You need to know the equation. You need to know this equation off by heart, and it is Li. You can just swap Li for Na if it's sodium, or K for potassium, or Cs for cesium. You get the idea. Rb for rubidium. You just swap it, but Li plus H2O, and that goes to LiOH plus hydrogen. So You need to know that equation off by heart. Is that balanced? No, it's not. So I need to balance it. I've got 3 hydrogens here. What I want to do is make that even to make it more even to balance. So I multiply all of that by 2, slap a 2 there, slap a 2 there, and now it's balanced. Now the state symbols. So very 100% tomorrow, 100% strike me down with lightning if it doesn't happen. You're going to be asked to give 2 observations for a chemical reaction, okay? So we've got solid and we've got water. They're solid, look, solid in water. What do we observe? I can't say I can see aqueous form or I can see a solution form. You can't see that because solutions are colourless. So you can't actually see that. What do you mean ink to maths? Yeah, whatever. But I can see bubbles of gas. So you will see bubbles of gas. So if you see a G, you will see bubbles of gas. And guess what? There's no S over this side of the arrow. So you will see a solid disappear. You don't need to get funky and think, oh, you just say, I'll see the solid disappear or the silver metal disappear. In any reaction, if you see a solid and then on the other side there isn't one, just say the solid disappears. Boom, mark. If there's a gas formed, you'll see bubbles of the gas. Okay, coolio. Right, now, if you test this with indicator paper, it comes out purple. Who can tell me why, if I drop some universal indicator, my lithium hydroxide is going to go purple? What is responsible for making my lithium hydroxide purple? It's alkaline, thank you, but what ion makes it alkaline? And hence, that's why we call them the alkaline metals. What ion, peeps? Boom! Truth hurts. Hit it with the OH minus. OH minus is the ion. That is going to make that alkaline, okay? So, if we're dealing with acids, it's H+, but with the alkaline metals, they always release hydroxide ions in solution. And so, that is what makes it alkaline. And you'll find that when you test it with litmus paper, it will go red to blue. If you put red litmus paper in there, it will go blue. If you use universal indicator, it's going to go blue anywhere up to purple, depending on how strong. But the alkali metals make strong alkaline, like pH 12, 13, 14. So it's going to be like more dark blue to purple. Okay, let's do a question, peeps. Rubidium is below potassium in group 1. Rubidium and potassium are added to water. Predict one observation you would see that shows that rubidium is more reactive than potassium. So, think back to the picture we just looked at. What would you see more of if rubidium, they're telling you rubidium is more reactive. Give one observation, just one thing you would see more of. I guess you can't say, oh, I'll see more solution formed, because you can't see that. What could you see more? Explosion, bubbles, yeah, more bubbles. That is the easiest answer to go for, right? More bubbles of gas. You don't even really need to say of gas. Effervescence, more fizzing are alternative explanations for that. Move around more on the surface, but that's a bit long, but move around more. You might say a more violent reaction, and they might give you that for the violence. What they mean by that is bubbles, flame, a bigger flame. Now, they're not asking you to guess the colour of rubidium's flame. I don't even know what the colour of rubidium's flame is. So they're not asking you to know that. That's outside of your spec. But you might see a bigger flame, more heat, higher temperature. It's going to release more heat. It's going to be more exothermic. Right, now we need to get onto this one, peeps. And this is, why is rubidium more reactive than potassium? Come on, pen, don't fail me now. Rubidium, why is it more reactive than potassium? Well, let's compare the two, right? Potassium, I'm not drawing the right amount of shells, but rubidium is further down the group. As you go down the group, they gain shells, right? So here's our lonely little electron on rubidium, and here's our lonely little electron on potassium. So now you've got to think, why would rubidium lose that electron more easily? And it's worth 3 marks. I will always try and say 4 things here. That's just the way it is. So what I'm going to do is say rubidium is larger. Now you can do the alternative answer and argue potassium's case. Potassium is smaller and go with the potassium, but I'm going with the rubidium explanation. Rubidium is larger, greater atomic radius if you want to get funky. More shells, more shielding, Oh my days, that is disgusting. More shells, more shielding. I mean, my order's not very chronological here. I really should have followed up rubidium is larger, electron further. Outer, I'm going to write an E for electron. Don't do that in your exam, but that's my shorthand. Outer electron, further. Oh my gosh, what does that say? From nucleus. Okay, so what is further from the nucleus? That means the nucleus is positive, the electron is negative. Less force of attraction, or less attraction. Shouldn't really say less force of attraction. Less attraction to nucleus. Right, now I'm saying like 6 things. Why am I doing that? Because I'm an idiot. So easier to lose electron. And that is, I haven't even pointed out that rubidium and potassium both want to lose an electron. I probably could have started off by saying group 1 metals, they both want to lose an electron. And now I want to tell you why rubidium loses an electron more easily. So easier to lose electron. That will be on the same marking point. You could say less energy needed to remove the electron or to lose the electron. Anywho, there we go. Right, and then this one, don't get it twisted. This is exactly the same as the equation I just did. Rb plus H2O. So you need to get to know it's going to form RbOH and H2. And then you're going to balance it. And once you know how to balance it, it's just 2, 2, 2 for the group 1. 2, 2, 2. There we go. And then state symbols. It doesn't say put the state symbols in, but solid, liquid, AQ, which is the alkaline solution, and bubbles are gas. Right, let's move on. This is comparing the alkaline metals with, maybe it's not, oh it is transition metal. There's a little transition metal question. Right, the figure below shows a piece of sodium. Sodium is Na on your periodic table. A piece of sodium being added to water, H2O, give 2 observations that could be seen when sodium is added to water. So what would you see if someone drops sodium in water? 2 observations. I know we've hammered this home. We're going to get off alkali metals, going to do the halogens, and then we're going to go to unit 2, which is bonding, because I know some of you are into your bond stuff. No diddy. Right, what are we doing here? Right, easy to lose 1 electron. Outer electron further away from, yeah, boom, boom, boom. Yep, flames, yellow flame, bubbles, boom. Yeah, love it, love it, love it. We're going to see bubbles, people. You're all over it. Awesome. Bubbles, yellow flame, great. Moving around, yeah, floating on the water because it's low density. All of these will tell us fizzing. Fizzing and bubbles are the same thing. Yellow flame, heat. Feel the heat. You're going to feel heat. Now, that one's quite difficult because you have to know it's exothermic, but a violent reaction like that, giving off a flame, it's giving out heat. So you're going to get a temperature rise. So all of those things are good. And floating around, moving around on the surface. So, and they move more quickly the more violent they get. Copper is a transition element. Sodium is in group 1, 2 boxes. Copper has a lower melting point. Copper is harder. Copper is less dense. Copper is less reactive. Copper is less strong. What would you tick? What would you tick? So, copper has a lower melting point. We won't make copper frying pans if they had a low melting point. All of the group 1 metals melt easily, right? They melt like easily. Wouldn't need a lot of heat. Gentle heating with a Bunsen burner would melt them straight away. Copper is harder. Yes, copper is harder. Copper is less dense. No, copper would sink. Take a 1p piece if you don't believe me, or a 2p piece. You people are probably too rich for that to have them, but I've got plenty of coppers hanging about. You just drop them in the sink and they'll sink to the bottom. Copper is less reactive. That is true. If you know your periodic table, if you know your reactivity series, copper's right at the bottom, just above silver and gold. And then over here, element R forms R2 plus and R3 plus. What section of the periodic table is it most likely to be? Where would we find an element that can be +2 and +3? We're going to find that in the transition metals. Okay, so if you're triple, you need to know that. Transition metals have multiple charges. Group 1, group 2, group 3 atoms, elements, they can't have multiple charges, okay? Like group 1 is only ever +1. Can't be +2. Group 2 is only ever +2. Can't be anything else but +2. Right, let's zing on. I have the halogens. The halogens are in group 7, and the elements are yellow fluorine gas. Right at the top is fluorine, and fluorine gas is yellow. Okay, it's a gas, and it's at the top of the group. Then we have our lovely chlorine. Chlorine is also a gas, and it's green in colour in its elemental form. If you dissolve these in water to form fluorine AQ, it's colourless, and chlorine AQ is yellow. They get lighter when you put them in water. Bromine is next up, Br2, and bromine is a liquid at room temperature, although it's volatile. I think it boils at like 40 degrees, so even in the room, there's been quite a lot of vapor around. You have to use that in a fume cupboard. Then over here, we have solid iodine, I2, and iodine is solid. I know you use iodine in biology to test for starch. Iodine is actually a grey solid, and it vaporizes into purple iodine gas, and when it vaporizes into iodine gas, we call that sublimation, and that's because of weak intermolecular forces in the iodine between the iodine molecules. So the reason why iodine sublimes is it only has weak intermolecular forces. All of them only have weak intermolecular forces. Fluorine's only got weak intermolecular forces, chlorine weak intermolecular forces, bromine weak intermolecular forces. Why is iodine solid and fluorine a gas? Because iodine is bigger, so it has slightly stronger intermolecular forces than fluorine, chlorine and bromine. So as you go down the group of any non-metal, group 5, 6, 7 and 0, from 5, 6, 7 and 0, as you go down, the boiling point increases, and this is shown by the halogens. Specifically why we learn about group 7 is because it clearly shows you their boiling points going up, because they go from gas to liquid to solid. And so it shows you that as they get bigger, as the molecules get bigger, you get bigger, you get a higher boiling point. Anyway, you get the same thing with the noble gases. Gonna have a little look at the noble gases. Yeah, let's have a look at the noble gases. What are my predictions for tomorrow?
What's your strategy?
Don't need any.
What's your prediction?
Prediction?
Yes, prediction.
Pain.
Sorry, folks, that's my prediction. Right, helium, neon, argon, krypton, xenon. Those are the noble gases. What you don't need to know hardly anything about these bad boys. They have a full outer shell. They're not reactive. Inert. They love that word. Inert. It means unreactive. So don't forget, noble gases are inert. Oh my gosh, they are inert, and inert means unreactive. They don't want to form compounds. They're noble and pure. They hang around on their own. They're the kid in the playground that's by themselves. They're like, no, I'm not mixing with nobody. I'm too good for you. So noble gases have a full outer shell. So you're going to link that to the fact that they don't react. They have a full outer shell. I'm on coffee today, by the way. Which I will have regular coffee breaks because I'm tired and then I get hyper. So inert, unreactive, full outer shell, so they don't react. This is why argon is great for like these guys. See this dude here? He's using, or she's using, don't know, under the helmet. He's using a really high temperature thing. The oxygen in the air could catch, when you're arc welding, the oxygen in the air could catch fire, and literally the air in the room could become a flame and you could burn your face off. So sometimes they do this in an argon atmosphere. They fill the room with argon, and then you can store precious things like holy books and old artifacts in krypton or neon atmosphere, because nothing can burn in there, and neon lighting as well. Okay, cool. Anyway, noble gases, all you need to know, full outer shell, and they're inert, unreactive. The one other thing you need to know is as you go down the group from helium to neon to argon to krypton to xenon, they are all gases, but they have increasing boiling points. Their boiling point increases because as we go down any non-metal group, the boiling points increase, okay? Because they get bigger and their intermolecular forces get stronger. Bosh! Okay, yeah, see if you can answer that. Argon has the atomic number 18. Explain why argon does not form compounds. Answer in terms of electrons. That will be a 2 marker. and should be nice and simple, guys. Why does argon not react? They're giving you this, you go like, oh, it's 288. Oh, 18, 288. What does it have? I'm going to say full outer shell of electrons. There you go. It's got a full outer shell of electrons, or I can say 8 electrons in outer shell. So does not need any more electrons. Okay, I might be overdoing it a bit there. I might even just write the word inert because I feel like it. Right, let's zing, 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 because we're going to go on to bonding in a second. Right, last question on noble gases, then I'm moving on to bonding. Oh, bonding, yeah. Yep, that's right. They can't gain or lose electrons. They've got a full outer shell. Absolutely. I'm doing bonding in a minute. Bonding I'm doing next. This is the end of Unit 1. Which is the correct statement about the noble gases? The noble gases all have atoms with 8 electrons in the outer shell. The noble gases have boiling points that increase going down the group. The noble gases have molecules with 2 atoms. The noble gases react with metals to form ionic compounds. What would you go for? Now, most people who make a mistake on this, some of you won't make a mistake, but some of you will make a mistake. I'd say the most common mistake answer is this one. Oh, noble gases, yeah, they all got 8 electrons. They haven't all got 8 electrons. That's why we call it group 0. They did used to call it group 8. It was called group 8 for a while, but that is the wrong answer. And the reason why it's the wrong answer is because of helium. Helium only has a shell with 2 bad boy electrons in it. So helium only has 2. The others all have 8. So then they said, we can't call it group 8 except for helium, so we'll call it group 0, meaning there are no electrons in the next shell after the outer one. All right. Right. The noble gases have boiling points that increase down the group. That is the correct answer. Of course, they are monatomic. So something I didn't mention when I was talking about the noble gases is noble gases are monatomic. Monatomic means made of 1 atom. And as you go down the group, like here's helium, here's another helium. So there are weak IMF, intermolecular forces between them. But as we go down the group and we get to like neon, neon is slightly bigger than helium. It's got an extra shell. And so the forces, there are more weak intermolecular forces. Therefore, it has a higher boiling point, more energy needed to break. Right, let's move on. We're getting into bonding. All right, so just remember there are 3 types of bonds in chemistry. You have ionic bonding, metallic bonding, and covalent bonding. Okay, you got ionic, metallic, covalent. Ionic is metal and non-metal. Metallic is just metal on its own. And covalent is when you have 2 non-metals. So the first thing you need to do is identify, because they sometimes don't tell you. In fact, more often on a higher paper, they ain't going to tell you this is ionic. They're going to give you something like sodium chloride. And you're going to go like, oh, sodium chloride? How am I supposed to know? Well, you should be able to know. You've got they've given you a periodic table. Easy enough, right? The metals are on the left. So the metals are on the left. And so sodium's a metal, chlorine's a non-metal. So therefore, sodium chloride is ionic because ionic are metal and non-metal. Now, ionic form what we call a giant ionic lattice. Look, we'd have our negative chlorine ions and our positive sodium ions, and they'd be together in this big bad giant ionic lattice. Now, you don't have to call it a giant ionic lattice. In AQA, they just want to hear the word, oh, what did I do there? That would be chlorine. In AQA, they just want to hear the word giant, folks. Giant will give you the mark. If they ask about structure, the word structure means you have to say giant or simple in your answer. So if they say, talk about the structure and bonding, you have to say giant or simple. And you might say both. But all ionic compounds, metal and non-metals, are giant structures. You don't need to use the word lattice, but a lattice is like that. It looks like a lattice, so you can use a lattice if you like. Now, what does this mean? This means if I want to melt a crystal of salt, of sodium chloride, I have to break every single one of these strong ionic bonds, and that is going to require tons of energy. So what we need to know about giant ionic substances, or any ionic substance, is that they have a giant structure with lots of strong ionic bonds. Okay, so lots of strong ionic bonds that require lots of energy to break. These are separate marking points. So why does sodium chloride have a high melting point? Giant ionic structure. Lots of strong ionic bonds require lots of energy to break. Boom! You've smashed out 3 marks. Now, if you can remember the definition of an ionic bond, the definition is, I'm not going to write it because I don't want to waste all that time. How have I got 2 chlorines next to each other? That makes no sense. Oh my God, this diagram is so crap. You wouldn't have 2 chlorines like that. They repel each other. Anyway, the definition of an ionic bond is an electrostatic force of attraction between oppositely charged ions. So take this Na plus and this Cl minus, this one here and this one here. They are opposite charges, so there is an electrostatic, but you don't need to say that in GCSE. You can just say the force of attraction between positive and negative ions or oppositely charged ions. Electrostatic you probably won't have to say, but if you can remember it, say it. Okay, so yeah, that's why they have a high melting point and boiling point. Now, they cannot conduct electricity because the ions are not free to move. What do you have to do to something like sodium chloride, an ionic compound, to make it conduct electricity? You can say electrostatic forces of attraction in GCSE and just say that there's lots of strong electrostatic forces of attraction between oppositely charged ions. These are called ionic bonds. Giant ionic structure, there are lots of them. Okay, which need lots of energy. The lots of energy is the easiest mark, and the word giant is the easiest mark. Now, they can't conduct electricity when solid, and this will come up, almost guaranteed to come up in your paper 1 exam at some point. Why did it not conduct electricity? And it will be an ionic solid they're talking about, and it's because the ions are not free to move. If we want to make it free to move, we have to dissolve it or in solution or melt it, make it molten. Now, we don't have to do the same for metallic. This is supposed to be a diagram of a metallic structure. So metallic structures, you will know that they are not ionic because sodium is just a metal. All metallic structures will have 1 word in the name, whereas ionic and covalent will have 2 words, i.e. sodium chloride, carbon dioxide is covalent. So they have 2 words in the name. I know some covalent like diamond, graphite are 1 word, but most of the time when you get a 1-worder, it's going to be just the name of a metal. So it could be silver, it could be aluminium. Soon as you see that, you can check your periodic table if you don't know about metals. Check the left-hand side. If it's on the left-hand side in the transition group or group 1, if it's in the transition metals or group 1, 2 or 3, it's a metallic structure. And it is giant. And we say the same thing. This, you're just going to change 1 word, the word ionic. So you're going to say lots of strong. If they ask you about structure and bonding, you're going to say it's giant, metallic, lots of strong metallic bonds, need lots of energy to break. Now, if it's a 4 marker, I want to describe that. Well, these are all, there's no negative ions. Okay, there's no negative ions. It's just positive metal ions. And this is supposed to be a depiction of like the delocalized electrons, this kind of mist that they've got going around. So this is supposed to be like the electrons from the outer shell of those metals have been booted out and are just sort of buzzing around the whole structure. And this makes metals able to conduct electricity. So I would not be surprised if tomorrow in your exam at some point they say explain why copper is a good conductor, explain why aluminium is a good conductor, explain why zinc is a good conductor, just any named metal, and you would say it has positive ions with a sea of delocalized electrons, or you just call them free electrons. AQA, you can call them free electrons, they'll allow that. Delocalized electrons. Now we don't stop there. We're going to say the sea of delocalized electrons can carry the charge. So if you imagine charge as like a little bit of energy or whatever, they can carry the charge through the structure. The electrons can. So you want to say it has positive metal ions surrounded by delocalized electrons which can carry the charge through the structure. Okay, and that is for delocalized electrons. Very similar answer to graphite. The only difference with graphite is we might say that each carbon atom has donated one of its electrons to the delocalized electrons. Okay. Does anyone have a question about metallic structures? No? Good. We're getting on to giant covalent. So I've been dealing with the giant structures because I just want to do the questions. I don't want to waffle too long about the content. But giant structures, remember, you've got diamond. So just remember, tomorrow you could get a question on diamond. How many bonds, how many atoms is each carbon atom? Oh! It's an allotrope of carbon. So diamond is an allotrope of carbon, which means a version of carbon. Each atom of carbon is bonded to how many others in diamond? Hopefully you know it's bonded to 4 others. Okay. Why does diamond probably got the highest, out of all the substances on Earth, it's probably got the highest natural melting point. I can't remember what it is, about 4,000 degrees. It's crazy, 4,300 or something. It's an absolute mental high melting point, okay? So each carbon atom is bonded to 4 others, and all you would say here is it's giant. Again, that word giant, 3 marks. Just easy marks. If they ask you about the structure of diamond, it's giant. You don't need to say lattice or macromolecular or any funky thing. You just say diamond has a giant structure. Then name the bonding. The bonding can be metallic, covalent, or ionic. Obviously, it's made of carbon. Carbon is a non-metal. And if you don't sniff a metal, then it's not metallic or ionic. So it is covalent. So we're going to say it's giant covalent. Lots of strong covalent bonds require lots of energy to break. You always need to say that. The moment you say something is giant, it needs lots of energy to break the bonds, which are strong. So for giant metallic, giant covalent, giant ionic, for ionic, metallic, and giant covalent substances, you're always going to say they're giant. They need lots of energy to break the bonds because the bonds are strong, and you'll probably smash out 3 marks on those. Even if you flop and name the bond wrong and you say, oh, it's giant ionic, lots of strong bonds, lots of energy to break. Even if it was covalent, they're going to allow you, and they're going to give you the fact that it's giant, and they're going to give you the fact that the bonds are strong and that there's lots of energy needed to break. So get that into your head. If you're going to write the word giant, you're going to follow it up with lots of strong bonds and lots of energy to break. Okay, so diamond, does it conduct electricity? No, it has no free ions and no delocalized electrons, unlike graphite. So just remember that graphite also has a high melting point, probably 1,000 degrees or 900 degrees, something, I don't know exactly, but also has a high melting point. But the difference is that if we graphite, by the way, comes in layers. That's the only difference between graphite and graphene. Graphene is a single layer of graphite, and they've been very handy in circuits and stuff, and in sports equipment. They tend to make stuff really strong, so graphene, but also conduct electricity. Right, you've got these hexagonal layers. Each carbon is only bonded to 3 others in graphite. So each carbon is bonded to 3 others. I know what some people are saying, but sir, look over here. That's only bonded to 2. What's going on there, right? That's because I have to end the diagram somewhere. This would go on and on and on. So it is bonded to 3 others. I just stopped the diagram. So this is bonded to another one. We just stopped the diagram. So always when you're looking, if you're worried about like how many bonds is it bonded to, check the center where they've drawn all the bonds, and then you can count them up, right? Because at some point they've got to stop the diagram. So yeah. Anywho, graphite is in layers which can slide. So the key points about graphite, it has layers. They can slide because of weak forces between the layers, which makes graphite a good lubricant, and is why pencil slides off when you're doing your artwork. Now, the other thing about graphite is that it has delocalized electrons. You don't have to say between the layers, but it has delocalized electrons. And the reason is the 4th electron that should be in a bond, like it is in diamond, is locked in a bond, is free in graphite, free to roam about. Whereas in diamond, the 4 electrons are in a covalent bond, where the 4 electrons in the outer shell of carbon, which is in group 4, are locked into bonds. In graphite, they're not. Like, so in graphite, each one is like that, and then there is a free electron which is just buzzing around. So graphite has delocalized electrons, which means it can carry charge through the structure and conduct electricity because each of the carbon atoms only has 3 bonds. Yeah, cool. Now, bada bada bing, bada bada bong. What else do we want to do? No, I haven't done quantitative yet. I didn't look yet at nanotubes or anything like that yet. I'm just kind of rambling through the bonding. What the hell is that a diagram of? I have no idea. So what I'm going to do, that's supposed to be an alloy, I think. I think I asked AI to make me a picture of an alloy. You know, problem is, if you don't have the time to really ask it questions, it starts making crap up. I asked it to draw me a picture of diamond. It gave it like 72 bonds. Okay, and yeah, it's going to take over the universe. Well, I better not insult it in case it's actually poised to take over and I'm there cussing it out. Right, let's do pure metal versus... So, on metals, which I didn't cover, pure metals, bosh, bish, bash, bish, bomb, boom. There's my pure metals. Look, lovely layers, fixed shape, structure, blah, blah, blah. You can punch a pure metal and the layers will slide over each other like so. You don't need to talk about weak forces between the layers. Don't do that. That's only in graphite. Don't talk about weak forces between the layers. The layers, pure metals are arranged in layers. The layers can slide. You do not need to talk about forces. Okay, now let's check out alloys. Alloys, the layers... And by the way, often they won't put the positive charge. That's me getting funky and showing you the positive charge. You don't have to put that. They won't always put that. Come on, give me the rubber. Where's the rubber? Oh my gosh. Oh no, forget that. Forget that. Forget that. Okay, I should have just stuck with it. All right, let's just leave it, leave it, leave it. They probably won't put the positive charge there, but an alloy is a mixture. They're not chemically bonded, but like, for example, steel, like what your knife and fork are made out of, steel, and parts of your car are made out of steel, contains carbon atoms. These black balls are carbon atoms amongst iron atoms. So that would actually be 2 plus or 3 plus. That's why I shouldn't even bother writing the pluses. But alloys, what do we want to know about alloys? They are harder. And the reason is 3 bullet point on alloys. They contain elements, oh my days, of different sizes. Hopefully you can see from my incredible drawing, level 4 GCSE art, that these elements are of different sizes. You can get excited and say they contain more than one element of different sizes if you want, but I ain't got that kind of room. So they contain elements of different sizes. You can then use a whole number of things for this. Layers, distorted. You can say deform the layers, disrupted the layers. The layers are out of shape. Don't be frightened to use normal, easy words if you can't think of the difficult word. Just say, oh, the layers are all bent out of shape, and so layers can't slide. This makes the alloy harder. So layers cannot slide. Now, what if they said, why is a pure metal softer? Then I could say, I could do the alloy thing and say, well, alloys are harder because they contain different elements. The layers get distorted and the layers can't slide. Whereas in a pure metal, it's only made of one element arranged in regular layers. The layers can slide. So you can kind of like do either one. Anyway, let's move on. Let's not stick around too long. Okay, who can explain to me, whip it out, daddy, whip. Oh my God, we've got a real, the Rage Beta. What a loser. Rage Beta, you are some kind of dweebicus.
Calm down, rude boy.
Dear oh dear, we've got a rude boy in the house. What do we reckon? Should we give him a slap?
Let's take a listen. Oh my God!
Yeah, we'll have to go to slap that geezer out of here, you know. Okay, don't worry. Okay, he's gone. We had to remove him. Obviously, when I'm whatever I'm saying, I have no idea. But you get the idea. He had to go, really, didn't he? Can't really have a geezer telling her, "Whip it out, daddy." You know, I mean, what a freak. Never mind.
And it's going to be a card for the Liverpool captain, and it's red. Deco, that's his second yellow. He's off.
We got rid of the rage beta, but you know what? Some of these dudes are back in seconds. They open another account. I don't know. They use their cousin and say, "Please, man, let me use your account. Let me use your account." There's a fat guy online, bald guy with glasses and a baseball cap, and he's sitting inside, and he's teaching chemistry. I got to get on there and cuss him. Pass me another bag of cheesy Watsits. Right. Graphite is made up of layers of graphene. Explain why graphite is a lubricant. So all we want to do is say it. Oh, it already told us it's layers. They won't give us a mark for layers. Now we want to say it has weak forces between layers. Damn. It has weak forces between layers, so layers can slide. There we go. It's got weak forces between the layers, so the layers can slide. So the 2 marks here were for slide and weak forces. If they hadn't mentioned layers, we might have got a mark for layers as well. It's arranged in layers. That's right, there are no covalent bonds, only weak intermolecular forces. You don't need to talk about delocalized electrons here. Sophia, you only talk about delocalized electrons when it's conduct electricity. So when it wants to conduct electricity, you can mention it with conduction of heat in physics as well. In fact, you can mention it in chemistry with conduction of heat. If it's said to you, and it won't say it about graphite, but if it said, why is copper a good conductor of heat? You'd say it has delocalized electrons. The electrons can carry thermal energy or heat through the structure. They collide with the positive ions and carry heat through the structure. If it asked you why is copper a good conductor of electricity, we would say it has delocalized electrons which carry charge through the structure. Now, there's a slight difference with graphite. Why is graphite a good conductor? It's very, very similar answer. We're just going to add one more thing in than we do with metals. We're going to say graphite has delocalized electrons that carry charge through the structure, but we want to say why it has delocalized electrons with graphite. They assume you know with metals, but we say that each carbon atom is only bonded to 3 others. Therefore, each carbon donates an electron to the sea of delocalized electrons. I've longed that out, but basically, each carbon atom is only bonded to 3 others. Therefore, it has delocalized electrons that carry charge. Boom, 3 marks for graphite. Now, the one not to get flipped and flopped and flappled up with is free ions. Free ions only come with ionic compounds, metal and non-metal compounds like sodium chloride, magnesium sulfate, zinc oxide. Those are known as ionic substances, and when you melt those, the ions are free to move and carry charge. However, when they're solid and locked in a giant structure, they are not free to move, so they don't carry charge. Right, that's the only time you want to mention free ions is when you're talking about ionic structures. Something else I want to just go about, we're on the bonding topic, is the polymers. Oh no, it's graphite. We're back with graphite. Oh, what the... This is a 6 marker, so test yourself out quickly. 2 marks for why is it a good conductor. I maybe say 3 marks actually for a good conductor. And then why is it soft and slippy? So they're 2 different things. Oh my God, there's a guy in the audience. Oh my days, we've got someone called at weirdo.com. I'm going to get rid of at weirdo.com while you guys try to come up with 3 marks as to why it's a good electrical conductor and why it's soft and slippy. Oh my days, why is it soft and slippy? I think at weirdo.com's getting very excited about those words soft and slippy. He's probably like getting excited in his little pants over there, so we better get rid of him, mate. Let's slap that geezer out as well.
Let's take a listen. Oh my God!
What is it about GCSE lives? I don't get this on the A level. I don't know what it is about GCSE lives, but they attract some serious weirdos. Serious freaks come out, man, sitting around eating their pizza on the internet looking to get into a chemistry GCSE live and talk rubbish. Anyway, never mind, we got exams to do, so we just slap that geezer out the live and we get on. Right, let's focus on getting through this. A good electrical conductor. So 3 points for the electrical conductor bit. Let's do that first. I want to say point one, why is it a good electrical conductor? This is the bit that you might miss. Don't beat yourself up if you get 5 out of 6. That's still pretty good. Each carbon, oh my days, look at that bad writing, bonded to 3 others. Problem when I kick these people out, they just come back like they just come back with another ID. So they borrow their friends, their uncles, their cousins, everyone they know's ID. It's like the most exciting thing that's happened to them. They're like, each carbon bonded to 3 others. So graphite has delocalized, oh my gosh, this writing is bad, electrons. The graphite has delocalized electrons. That's going to get us some marks. We've explained why it has delocalized electrons. And then I want to say delocalized electrons. I'm just going to write E, write electrons in your exam, carry charge through the structure. Oh my gosh. Oh my gosh, look at that. That is disgusting. That is seriously disgusting, that writing. Okay, so now I've covered why... Okay, we've covered the delocalized electrons bit. And they can carry charge. So you're kind of saying, yeah, they're giving you a mark for that. Oh my gosh, that's so bent. Right, come on. We can do this. And then we've... come on, where's my pen? Right, there. Delocalized electrons. Carbon is bonded to 3 others. Carry charge. That's 3 marks. Now we want to say why it's soft and slippy. That's the stuff that gets that guy excited, unfortunately. That's the kind of loser we got going on here. Right, graphite, we need to just mention, is arranged in layers. And that is a mark just for saying arranged in layers. And then what we want to say is weak. I'm going to write IMF, but you need to write intermolecular forces. You can just say weak forces between the layers. In fact, intermolecular forces is probably, they'll allow it, but that's probably a bad thing to say because graphite doesn't contain molecules. So how can it be molecular? So let's just say weak forces between layers. Just in case you get an examiner who's like, it doesn't contain molecules. You can't say weak intermolecular forces. And you might get that. So we don't want that. So graphite arranged in layers, weak forces between the layers. So we say layers can slide. If you want, you can say the forces are easy to break or the forces are overcome easily. And there we go. Bosh, 6 markers. Alloys is slightly different, peeps. Alloys isn't about weak forces. Alloys, you're just going to say, has different sized elements. They disrupt the layers or change the shape of the layers. So the layers, they can't slide because instead of being regular, one's bumpy, like they're bumpy, so they lock on each other. And the way to describe that is just to say alloys have different sized atoms or elements. You can say atoms or elements. Therefore, the layers are disrupted or deformed. They're not in the right shape. And therefore the layers cannot slide. And those are your 3 marks for why alloys are strong. Oh my God, we've got an alloy question right now. We will do a diamond question, definitely. We can do one. So, We'll do a diamond question if someone's predicted diamond. You know, I'm not into predictions because, like, you could sit here and be like, oh, I'm predicting diamonds coming up. Revise everything, peeps, but diamonds coming up. And then diamond comes up and people get on the chat and they're like, sir, man, you were right. Diamond came up. And I'm like, yeah, well, it's part of the syllabus. I can predict anything, really. You know, if I make 10 predictions, 5 of them are going to be right. So, kind of easy going, isn't it, really? They're going to ask you 50% of my predictions, so it's better to just revise all of it. Right, explain why alloy is harder than pure metal. So we just did this. So we're going to say only 2 marks, stingy gits. Different sized atoms, I'm going to say this time. It could say elements, quicker to write atoms. Different sized atoms I'm going to use the word disrupt, but you could say deform, and then layers. And then I want to say layers cannot slide. Bosh. 1, 2, 3. What percentage of atoms in the alloy is that atom X? This is just to add it up. I ain't going to do, what's that? That's 2 divided by, oh my gosh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I don't even know if I counted that right, guys, so I'm sorry if I got that wrong, but there we go. Let's move on. What type of substance is an alloy? A compound, an element, or mixture? Look, these are not chemically bonded, covalent, or ionic. They're actually a mixture. So you do need to know an alloy is a mixture. Oh my gosh. Oh my god. The loser's back, guys. Hey, look, I hit you with a diamond. Why is diamond hard and why is graphene strong? But we can add to diamond. We'll add some other explanations. We're going to do why is diamond hard, and then I'm going to put why. I'm going to put everything about diamond so we can get it. Why is diamond hard? Why does diamond not conduct electricity? You need to know that as well. And then I'm going to add in one down here. Why? And all of these could be 3 or 4 markers. Okay, they could all be 3 marks or 4 marks. So why does diamond have a high MPT, guys? Melting point. And that could all, these could all be 3 or 4 markers individually. It just depends on question to question. Let me deal with this idiot while you have a go at that. Why is diamond hard? And that's the same answer, by the way. Diamond being hard is the same answer as why does it have a higher melting point? And this guy, 2F3Q or whatever, I think he's pretty hard as well because he's an absolute weirdo. So we're going to chuck him out. Ustinko's going to drag down the grades. Yeah, this guy is obviously a total weirdo. Like I said, you'll get these people and they come on every year. I think like they're like a little Stan fan, you know, like the little stalkers. I think like a little stalk, like you get these weird stalkers. They just love it, don't they? And I don't even know if like kicking them out is the thing because, you know, they seem to just try and come back. That what you're going to do? What are you going to do when you got some total plums like that? Okay, he's going to be back in a minute. Anyway, got rid of him for now. Boom. Boom. All right, folks. So we're looking at diamond here. Not sure until I get a bit tired. So we're looking at diamond here. Why is diamond hard? I've got to get rid of that guy. I mean, what a weirdo, eh? I think he's a bit of a stalker. You know, he's sitting there on a Sunday night, probably been crying, stuff like that. And then he thinks, oh, look, there's people on live. I can come on and say some rude things and make myself excited. He's probably, you know, yeah, who knows? Weird guy. Right, explain why diamond is hard. It's the same as why it's high melting point. So what I'm going to do here, and that says 2 marks, I'm going to bust out 4 bullet points because I ain't hitting those 2 marks. So I'm going to say giant, because often these are 4 markers. Giant covalent. Now you can say lattice structure, whatever you want. I'm keeping it simple. Giant covalent. Lots of strong covalent bonds. And I'm going to bust out lots of energy to break. And that is going to explain why it's hard, because it takes a lot of energy to break. But here's the unique thing, because that could be any giant covalent compound. That could be silicon dioxide, SiO2. That is a giant covalent compound that has white and black balls in the diagram, and it looks just like diamond. But what we want to uniquely say about diamond is that each C atom bonded to 4 others. Don't be afraid to repeat that if you get more than one question on diamond. Just slap that in there. they are not taking marks off for you saying a correct fact. You cannot lose marks for saying a correct fact. Like if you're giving the right answers that are on the mark scheme and you say something correct, you could lose a mark if you say, yeah, each carbon atom bonded to 3 others. Then, yeah, you're going to lose a mark. You've said something incorrect. But the worst they'll do is say ignore, on the mark scheme, it will say ignore carbon is bonded to 4 others, because that's not what they were looking for this answer. But they're not going to take the marks off. So I'm going to put all of it. I'm going to put it's a giant covalent. Covalent bonds are strong. There are lots of bonds. I said lots of strong bonds. I want to make sure that they know there's lots and they're strong. And then I'm saying each carbon is bonded to 4 others, because that's a unique thing for diamond. Now, why does it not conduct electricity? If we're on that tip, we want to say it has no delocalized electrons. Guess what I'm going to do? I'm going to repeat the 4 bond here. So I'm going to repeat this. Why does it have no delocalized electrons? I'm going to give you the reason. Because each carbon atom bonded to 4 others. So it's the exact opposite of graphite, where it has a free electron. There are no free electrons because each carbon is bonded to 4 others. So I'm showing the examiner I know this. So yes, they may include these 2 questions together. They might say, like, explain why diamond is hard and why it doesn't conduct electricity. Or they may say, explain why diamond has a high melting point and why it doesn't conduct electricity. And it would be the same answer for both. So the answer for hard and high melting point are the same. So I'm not going to write out the high melting point one. It would be the same. Giant covalent, lots of strong covalent bonds. The only thing I could add there that I don't have the space is if I want to show off, I might add what a covalent bond is. It's an electrostatic attraction. So do remember that a covalent bond is an electrostatic, I mean, they very rarely ask for this in AQA, but it's an electrostatic attraction. Electrostatic force, I missed out the word force, but electrostatic attraction between nuclei, oh my good gosh, and shared pairs of electrons, which I can't be bothered to write. So that's the definition of a covalent bond. It's the electrostatic force of attraction between nuclei and shared pairs of electrons. Sometimes you might have a 6 marker and you can work that in there. Now, why is graphene strong? There's no point. That graphene, oh geez, why is there no point in me answering that? Because it's the same as why diamond is strong, except for you don't need to say the bit about the carbons. Okay, why is it strong? What kind of structure is that? It's giant. What does that mean? Lots of strong bonds. I'm going to name them covalent bonds. Lots of energy needed to break. Okay? To overcome, to break, to snap, to split the bonds. Cool. Let's move on. Yes, Michelle Emmanuel, Buckminster fullerene is an allotrope of carbon, but buckyballs are a simple covalent compound in that they're only made of like 60 atoms, whereas say a sheet of graphene might have 1 million atoms in it, or 1 trillion atoms. One diamond on a wedding ring or an engagement ring has more atoms than 100 lifetimes of human beings could count. They'd all die. If you were born and you started counting 1, 2, 3, 4, and then you lived to 100 and you died and you passed on the number to your grandchildren and they carried on and their grandchildren, you still never get to the end of it. There's trillions of atoms in a diamond, all locked in that. That's why it requires so much energy to melt. Now, buckyballs are like these things here. They look like a football, and nanotubes came later because we can bend the buckyballs and we can bend these graphene sheets of graphene and graphite into nanotubes. And what do you have to know about buckyballs and nanotubes? Well, buckyballs make good lubricants. Why do buckyballs make good lubricants? They have weak forces between the buckyballs. Weak. Why am I writing in green on that background? No one can see that, you utter dipstick. So, yeah, they got weak forces here, guys, between the balls. The guy I kicked out would probably like that terminology, but yeah, they got weak forces here. However, don't get it twisted. These are strong covalent bonds. Covalent bonds are very strong. only beat by ionic bonds. Strong covalent bonds there, but there's weak forces. So that means the balls can slide. So what we want to say is the balls can move around each other. Balls can slide around each other. Now, when you were little, you probably jumped in a ball pit before. You were at one of those play centres and you jumped in a ball pit. That's basically saying why buckyballs slide. Imagine a ball pit that like a kid jumps in and all the coloured balls are moving around. That's like buckyballs. They're not stuck to each other. But the actual ball itself is held together by strong bonds. But between each ball is weak forces. So it makes them a good lubricant. They're good. They slip and slide over each other. Now, nanotubes, same thing. They can slide over each other because there would be weak forces between the nanotubes. However, nanotubes can conduct electricity because they have delocalized electrons. Buckyballs, you can't really conduct electricity because the balls aren't attached to each other. They've only got weak forces between them, so you can't really conduct electricity there. But you can use them in medicine, so you do need to know just off the dome that buckyballs can be used as a nano cage to hold medicines and deliver medicines to parts of the body and stuff like that. Nanotubes the same as well. You can lock things in. And with all of nanotechnology, talking of nanotech, all of nanotechnology, they have a large surface area to volume ratio, and that's one of the things that gives them their special chemical properties when we talk about nanotech. Anywho, here is a question on nanotubes and buckyballs. You might want to have a go and see if you can answer it. There are indeed. Yeah, I can. Just to remind you of, I can remind you about bio-leaching. It's more of a paper 2 topic for AQA, but bio-leaching is when we take scrap metal and, it's when we take low quality ores, low grade ores of copper, and we let bacteria grow on them. And the bacteria create a leachate. They suck up the ions and they create a leachate. A leachate is a solution that contains copper ions. And then what we do is we do electrolysis and we remove the copper. And Bob's your uncle, Fanny's your aunt. You've got some copper from a low grade ore. Now, the reason why we do this on low grade ores. Low grade ores is normally too much money. It costs too much money to melt the ore and do electrolysis on it that way. You might spend like £10,000 melting a rock and you only get £2,000 worth of copper out of it. So you've just lost £8,000. Your company's going to go out of business. So a low grade ore doesn't have enough copper in it to justify melting the rock. So what we do is we get bacteria to live on it, suck up the copper, and then they leak out a liquid called a leachate that contains the copper ions, and then we do electrolysis to remove them. So the 3 bullet points for bioleaching are bacteria, leachate, electrolysis. So they're the 3 bullet points in your head. You just want to say bacteria, leachate, electrolysis. Bacteria absorb the copper ions, create a leachate, and then we do electrolysis to remove them. You can say we do displacement to remove them as well. Phytomining is slightly different. Phytomining, instead of bacteria, we get a plant to suck up ions, and the plant sucks up the ions, and then we burn the plant. I know it's a bit mean, but we burn the plant, and inside the ash are the metal ions. So we make that into a solution and then do electrolysis or displacement with scrap iron. Now, bada bada bing, bada bada boom, bada bada bang. The structure and bonding in a carbon nanotube are similar to graphene. Carbon nanotubes are used in electronics because they conduct electricity. Why do they conduct electricity? You know the coup. They've got delocalized electrons that carry charge. Boom. A lubricant is a substance that allows, now, if it says it's similar to graphite, I want to add in each carbon atom is only bonded to 3 others. Let's have a look. Look, you can see that with them hexagons. Look, each carbon atom is only bonded to 3 others, hence it has delocalized electrons which carry charge through the tube. Boom. A lubricant is a substance that allows materials to move over each other easily. It suggests why Buckminster fullerene is a good lubricant. It has weak forces between the balls, or the Buckminster fullerene balls, or between the molecules, hence the molecules can move around each other or slide over each other. And then here, why are nanoparticles effective in very small quantities? Tick one box. What's the special thing you need to remember about nanoparticles? And a special thing you need to remember is that nanoparticles have a high surface area to volume ratio. One advantage of using nanoparticles in sun cream is that a small amount covers a large area. Okay, so you only need a little volume or a little amount to cover a large area. One disadvantage of using nanoparticles, we're not sure about possible, I don't know, future side effects. Maybe I get a mark for that, right? They can enter cells. That's really crap. They can enter cells. Oh, I can't bother to write. Yeah, basically, nanoparticles are so small that people are worried about breathing them in, them getting into your lung cells, mutations, cause cancer, things like that. We don't know. They're a new technology, and so we don't know if there are any long-term side effects because we haven't been using them for long enough to know. Anywho, I couldn't be bothered to write that all out. You do need to know about this. Describe the structure and bonding in a thermo-softening polymer and explain why thermo-softening polymers melt when heated for marks. I know what you're thinking. So this paper 2, no? No, it's paper 1 if you're TRIPS. You've got to know the difference between thermo-softening and thermo-setting polymers. So if you're TRIPS, you need to know that. If you're AQA and you're TRIPS, you need to know that for paper 1 as well. Well, you just need to know that polymers have weak intermolecular forces. So the idea, I'm going to go here and just talk for it. Thermo-softening polymers have weak intermolecular forces between the layers. You don't need to know that Van der Waals stuff. They have weak intermolecular forces between the layers, which don't take a lot of energy to break, whereas thermosetting polymers have stronger forces or covalent bonds known as cross-links between the layers, which require lots of energy to break. Let's get off of that. There's another one that came up. Polyethylene is a thermoplastic that softens easily when heated. Suggest and explain how the structure of PX changes this property. So you can see there are no cross-links. When you have this PEX, it now has cross-links between the layers. So we would say it's going to make it harder and stronger and higher melting point and less soft because it has cross-links between the layers. Okay, this is one that comes up in paper 1 quite a bit. So it's come up like 4 times for AQA. Oh my gosh. Magnesium oxide contains magnesium ions and oxide ions. Describe as fully as you can what happens when magnesium atoms react with oxygen atoms to produce magnesium oxide. This has come up like 4 times out of 7. So you've got like about a 60% chance this is coming up, something like that. This kind of question is coming up. So what you want to do here is you want to recognize, they've already given us +2, right? Magnesium's in group 2. Therefore, it had 2 electrons in its outer shell. It's a metal, and oxygen is a non-metal, and oxygen has 6 in the outer shell. You don't need to draw a diagram. But this means that magnesium is going to give 2 electrons to oxygen. And we just need to word that and explain what happens after. So afterwards, they're going to become like this. You're going to end up with an Mg, and they told us this in the question, Mg2 plus and O2 minus. So we're not going to get marks for that. Most of the time they don't tell you, and you'll actually get marks for that. So you'll actually get marks for giving the ionic charges, but this one they're not giving you the marks for. So that's fine. Right, what we're going to do here is, oh, I screwed that up, didn't I? Never mind. Okay, so what we're going to do here is just put this into words, and we're going to say Mg gives 2 electrons to oxygen. And believe it or not, that's 2 marks. So that's 2 marks because you've said electrons go from magnesium to oxygen and you've given the correct amount, which is 2. So, and now I want to say they both have full outer shells. Come on, T. They both have full outer shells. You could say they're both stable if you like. You could give their they're actually going to be, because magnesium was 282 and oxygen was 26, and afterwards their electronic structure is going to be 2,8. Oh my gosh, that came out a bit weird. And that is going to be 2,8. So they're going to have identical electronic structures. You could point that out. Normally, I would point this out. I would definitely normally say magnesium will be a 2+ ion, oxygen will be a 2- ion. But guess what? An oxide ion. But they've already told us that, so we probably won't get marks for that. Cool. Right, let's bang on and do some practicals. All right, we're going to go through how to make a salt. This is a core practical that could come up, and yeah, let's go through that. What I'm going to do quickly is just go and grab myself a coffee. So I'm going to be back in 2 minutes. Guys, don't forget to hit the like for me.
If you push the button,
Like me.
Would you like it?
Like.
do it. Do it.
Do it.
I'm back. That was quick. Yeah, I decided against the coffee break. I'm having water instead. A bit better. So, ooh, best of the pro. Sounds pretty good. Yeah, no, what you're saying, best for pro says heat the acid, keep adding the metal oxide till it's in excess, then filter the excess, heat gently and leave to crystallize. Boom! You get quite a few marks for that, but there's a little bit more you can have for 6. So, what we're going to do is go through it. And what they're looking for here, peeps, but you are basically on the right track with that. So, let me zang through. What the arse is going on with this, man? Come on, sort it out, Tom. Right, what we're going to do. So we want to make pure. Check that pure. Check the dry. You need to mention the dry, right? They're giving you the clue there. They want you to mention why did they say dry? Why did they say pure? You kind of done that. So, and they gave us the name of the salt. So it's not just any salt. They gave us the name. And they didn't tell us the name of the acid. That means they're like fishing. Oh, they didn't tell us the name of the oxide. They're fishing for the name of the oxide and the acid. They're kind of telling you there's some bonus marks if you can work out the name of the oxide and the acid. Well, if it's a sulfate salt, we're going to use sulfuric acid. And the metal is going to have to be magnesium oxide. So we're going to say add magnesium oxide. I'm just going to write the symbols, guys. But yeah, to H2SO4. I'm not putting the state symbols or anything. You can say warm it. That is sometimes on the mark scheme separately. So add the two together, mix. These are probably all wrapped up in the same thing. So add magnesium oxide and sulfuric acid, warm it. And then what do we want to do? What do we want to do? What do we want to do? Add. You always add your oxide carbonate, your base. Remember, this is our insoluble base. Insoluble means it doesn't disappear when you add it. It won't disappear in water. So you're going to add your magnesium oxide base. It will disappear as it reacts, but when it finishes, it's going to float in the water that's left over. So add magnesium oxide base until excess. Key. Then what we're going to do is say filter. Now, don't be frightened to add a couple of details. You never know when they're going to get cheeky and say you need to mention funnel, filter paper, filtration. So just, yeah, filter with a funnel and filter paper if you can remember. If you can't, don't worry, because sometimes they just want filter. What are you filtering? You're filtering off excess base. In this case, excess base is MgO. Now, what are you left with? Well, think about it. When we started, we had MgO and H2SO4, acid and base. After all the acid has been used up, all we are left with is H2O and MgSO4, magnesium sulfate, and our excess base. Well, guess what? We just filtered off the excess base, right? We got rid of that. So we're now left with just H2O, and MgSO4. They're asking you how can you get the MgSO4 out on its own. So we just want the salt. So what you're going to do then is gently evaporate some water. Oh my gosh. Evaporate some H2O. I can't be bothered to write water. So you're going to gently evaporate some water until you see crystals. Then leave, oh my days, this is long, in a cool, dry place for crystallization. Oh my gosh. Crystallization to occur. Okay, and then at the end I would say dry with paper towel. I know it sounds stupid, that's always a mark on the salt practical, dry with a paper towel. And the free mark you get there, they actually give it to you in the question by using the word dry. Where are you? Yeah, it's up there, dry. Anyway, lovely jubbly. You might get a couple of marks if you drew a diagram. You don't need to draw a diagram, just put it in words. Yeah, a drying oven on a very low temperature. You could dry it in an oven on a low temperature. Yeah, you could do. Right. Oh my gosh. You've got the reactivity series. What do we want to talk about here? Watch out, guys. They sometimes do a little practical on this. They sometimes bust out a little practical, which they've done a few times in AQA, where they say, what should we say? I'm going to give you a question for 6 marks. This would be a nice one though, wouldn't it? Describe an experiment to find the order of reactivity of 4 unknown metals, and we're going to call them W, X, Y, Z, and we're going to give you 6 bad boy marks. So bullet point, how would you do that? Where's my charge on this thing? Oh, this is like the crappiest charging thing ever. Okay, listen, what you would do here, this one comes up occasionally. So you normally, they give you some equipment as well. You're going to get acid. Use the same volume of acid. So put acid in here. Remember, metals react with acid. They release hydrogen gas. So you're going to get acid, acid, acid. If you're not changing the you want to keep conc the same. So you've got something called control variables. So you've got to think about your control variables. Keep the volume of acid the same. Keep the concentration the same. Keep the temperature the same. We don't want to heat it up. We want to keep the temperature the same. Now, you're going to add W, X, Y, and Z. And then you could do, I'm going to count the bubbles in a minute. Or even better, somebody did mention temperature. You're going to put a thermometer in and measure the temperature change. So you could bash a thermometer in and measure the temperature change. You're going to repeat 3 times and find the mean temperature change for each metal in acid. The one that gives off the highest change in temperature is going to be the most reactive metal. Now, we do need to say keep the same size of metal and the surface area of metal the same mass of metal, sorry, not size, mass. You're going to use a scale, measure the mass. You're going to use a measuring cylinder and measure the volume of the acid, and you're going to use the same conc of acid. And yeah, you're going to keep the initial starting temperature the same. And there we go. You can do displacement with copper sulfate solution. So what you're going to do, yeah, you could do that. There's all different ways you could do this. You could catch the gas in a gas syringe. You could count the bubbles, and you can then rank them in order, you know, most to least. That has come up a few times, even though it's not a core practical. I've just noticed in AQA that's come up a few times. Now, if you heat them up, you don't need to heat them up. If you heat them up, then you don't know how quickly they're reacting. You measure the heat coming off. They're going to be exothermic and release heat, and you can measure the amount of heat coming off. If you start adding heat, how do you know which one's more reactive? Maybe you're heating one more than the other. How do you keep the heat the same? So you don't want to heat them up. You're trying to find out which one reacts more with the acid. If you add heat, you're increasing the collision frequency and stuff. You're affecting the rate of reaction, and therefore that's going to make it difficult. Is there anything anybody else wants to go over? Or is everyone done? Is there anything people want to go over? Let me go through some exothermic, endothermic energy profiles. So, got an exothermic energy profile. Does anybody know what goes here? Oh, let me label it, and then you can tell me what A, B, and C are. Actually, I'm just going to talk you through it. Right, so here is the reactants. This is the reactants. This is the products. And you would have here energy, and along the bottom time or progress, like of the reaction. So here's our energy, and then woo, our energy goes up. And we call this, we need to put energy in to get the reaction started. You could have a bucket of petrol in front of you. My God, sir, petrol's flammable. It burns in oxygen. Yes, but it won't burn unless someone throws a match in. Otherwise, every time someone went to the petrol station, the air is touching the petrol all day long. The air is going in your car, and oxygen is touching the petrol in your car. It's not just blowing up like they stupidly do in the movies when a car crash happens. Cars just explode in the movies. That doesn't happen. You need activation energy to get the reaction started between chemicals. So that's like lighting a match and throwing it in. So this is your activation energy. You can write that as EA, energy of activation, or AE, some people write it. So that's the activation energy, and the arrow is always going up because you're putting the energy in for activation. Now, in an exothermic reaction, the energy change in the reaction shows our line is going down. This is the energy change, sometimes written as delta H, or you can just say the energy change in the reaction, and that's always down. Okay, so nice. You have the reactants there, products there. That's the activation energy, and that is delta H. And this is exothermic. Now, how do we know it's exothermic? The products are at a lower energy level than the reactants. They have released energy to the environment, causing the air and the surroundings and the solution to get warmer. All right, let's look at the opposite one. You have an endothermic reaction. So the only difference here, you've got your reactants and products there, and you've got your arrow going up of the energy that got put in. So the arrow goes upwards. And let's just test you out with that. So what do labels A, B, and C represent on the figure above? What would you say are A, B, and C? Are you talking about the half equations? No, activation energy. Yeah, oh yeah, nice. A is so A is going to be just energy. No, progress of reaction, sorry. A is progress of reaction. They're talking about how do you label the graph. This is energy, always up here. You can call that time or progress, like how long they react. There's energy there. B is activation energy. C is products. Okay, and they didn't have the energy of the reaction. Overall, oh sugar, the overall energy change, this one would be this. The overall energy change is the difference between the activation energy and the energy released there. Okay. Okay, let's do a quick bond calculation. There hasn't been an exam where they don't ask you a bond calculation. So what are you going to do here? They've said in the reaction, the energy released, and you have to check what they're writing here. The table below shows some of the bond energies in this reaction. In the reaction, the energy released, so always tag up and write over your paper, forming new bonds is 1034, just for those of you that can't see that. It's 1034 greater than the energy needed to break bonds. That energy released is always exothermic. So the energy released is exothermic. Calculate the bond energy for X. Now, if this was nice and easy and 3 marks, they would have just said calculate the overall energy change. And that's always super easy because all you're going to do is change this to a minus, and you want to do reactants minus products. And that normally equals delta H, which is the energy change. But we've been told the energy change is minus 1034. And how do we know it's minus? Because they said it was energy released. Cool. So what we want to do here is write all that we know down. So check each of these. SH is worth 364. And there are 2 of them. And then there's the big 2 there, the multiplier. So in an essence, I want to go 2 times 364 plus 364. But I could just say 4 times 364. And that's because there are 4 HS bonds above. And for those of you that are like, so I don't get what there's 4 HS, they're saying there's a 2 there. So they're saying that we have, when you see a 2, it means we have 2 lots. So that's like that. So there's 4 of them, and that's why you got 4 times 364. Now we want to add that to 300, and that is 498, and there are 3 of them. So we want to add that to bish bash 3 times 498. Oh my God. And then we're going to write minus in our equation, and we're going to do 2 OH's, but look, there's a big fat 2 there. So I'm just going to do 4 times 464 minus 4 times 464. And why am I doing that? Because it's HO, HO, and there's a big 2. So it means that the big 2 tells you, it's a coefficient, that you have that. That means I've got 1 of those and 1 of those. That counts as 1, that counts as 1, that counts as 1, that counts as 1. So it's 4 of those OH bonds. Nice. Next, I want to look here, and this is the one we don't know, but I do need to know how many of them there are. And again, we've got a big fat 2, so it means I've got 4 of these bonds, but I don't know it, so I'm going to leave it algebraic. You love a bit of algebra. I'm going to put 4x, and then we're going to put equals minus 1034, and then you're a better person than me if you can rearrange that. So you're going to rearrange that, and you're going to smash out 5 marks. But remember, take your time. If you're someone who doesn't always get 5 marks, you take your time, because on the mark scheme, they want to see some of the calculations. So if you've done 4 times 364 and added it to that, you're going to get a separate mark just for doing that. So let's smash that out and write them, build them up. So 4 times 364, and that gives me, oh my gosh, oh, don't do that. See, I clicked the wrong thing. 1456, and then I'm going to add that to 3 times 498, and that gives me 1494. 1494. We're going to smash those together, and they are going to give me 1494. 1494 plus 1456. So what I'm saying is, even though this I'm super slow and probably making mistakes, 2950, the examiner's going to see that and be like, yes, they got 2950. So even if you flopped and you might be overconfident, someone who's overconfident, and you think, oh, I can't mess this up, trust me, well, I mess this up all the time with calculations. I put the wrong thing in my calculator. So we're then going to minus 1856. That's that there. That is probably going to be a mark on the mark scheme. So just doing 4 times 464. And then I want to plus that to 4x, and then equals minus 1034. And now what we want to do is we want to solve this bad boy. So I'm going to I'm going to sort these two out. So I just got one number. So I'm going to go 2950 minus 1856. And I'm going to get, oh my days, come on Tom, sort it out mate. I'm going to get 1094 plus 4x equals minus 1034. Now what I'm going to do, what we're going to do now, folks, we're going to take 1094 from each side. So I'm going to go minus 1034 minus 1094 equals, oh, come on, Tom, minus 1034 minus 1094. By taking that from each side, oh gosh, I hope I got this right. This looks disgustingly bad. That equals 4x equal to, oh, I hope I got this right, folks. Has anyone else got this? X is 532. I should hope so. With my rearrangement, who knows? Yes, X, and now you might say, sir, but you got X equals minus 532. That's because I'm an idiot and didn't do something correct. Look there, these numbers, these bond energies, they're going to say, in the mark scheme, they're going to say ignore minus or plus. So I'm going to just write 532 there. Okay, guys. Bond breaking, the energy needed to break the bond is always a positive energy, but I did something wrong with my rearranging, but we got there in the end. We got the answer. So we're going to do 2128 divided by 4, bish bash bosh. Okay. Yeah, energy's released, so it's exothermic. We know that's why that was minus 1034, because energy was released. Now, let's zing. Oh gosh, we don't want to do another one of those or another one of those. The student made 2 errors when drawing the reaction profile. Describe the 2 errors. Well, the progress of the reaction is fine. The energy is fine. Can anyone spot an error here? We didn't really, I should have read the stem of the question. I don't know if this was an exothermic or endothermic. 6 marker titration electrolysis. All right. Let me zing on. Let me zing. Zing. Bada bada bing. Oh, no, that's a fuel cell. Let's go electrolysis. Let's do a quick electrolysis question. Let me find an electrolysis question for you. Let me find you an electrolysis. We'll do a quick electrolysis and then a titration. No, titration's not in there. Electrolysis is, but titration is not in combined. Higher. What I want to do, flip over there. That's where I got me electrolysis examination questions. Hold on one sec, peeps. Hold on. let's do an electrolysis question. No, structure and bonding. Where are you? Electrolysis. Oh, would have been nice if I hadn't scribbled all over all of these like a plum. Yeah, I've kind of scribbled all over these. Let's give me 1 second. What else did people say? What I want to do, give me a sec. Oh, this is all from a live I did on electrolysis before. Okay, where's the questions though? That's the thing. Yeah. I'll do electrolysis and titration. Oh man, where's the quick way to just? Oh, I know what I do. Do that T, and then new slide. Bish bash bosh. Okay, we'll do that. And give me 2 seconds. I'm just preparing a couple of questions for you guys, and then we'll smash through electrolysis. That's not really what the doctor ordered. La da 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 da. Dee 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 dee. Oh my gosh. Come on, Tom, sort it out, mate. Where are we? Yeah, well, I'll go through some questions for you with electrolysis, and then I ain't going to do the full teach the whole thing because that'll take like just about forever. Right, I don't want to do that one. What about that one? Okay, I might do that one. Yeah. Okay, let's do some electrolysis. Where's another easy peasy pudding and pie one, and then we'll do a difficult one. Okay, yeah. Got that. What about that one? Yeah, that one is difficult. Squifficult. Let's go. All right. Enough messing about. I'm gonna get on it now. Here we go. I just had to like fiddle. No dids. Oh, what happened there? Yeah, there is a practical on energy changes that you have to remember as well. You got a practical where you have like a polystyrene cup. Always remember that's an insulator, so it makes it more accurate. You do like a reaction. You mix an acid and a base, and you're going to measure the temperature change, and to find out if it's exothermic or endothermic. And you want a lid with a thermometer pushed through it, and you want to make sure that you measure the heat that's coming out, so you can tell if it's exothermic if the temperature goes up, and you can tell if it's endothermic if the temperature goes down. You want to measure the temperature change over like 5 minutes or whatever, and you can do that. You can change the variables and then measure the temperature change, and you can plot that on a graph and work out the initial or the final temperature by extending the graph. But I ain't going through that right now. I'm going to go through electrolysis. So solid calcium chloride cannot be electrolyzed. So why is it that solid calcium chloride cannot be electrolyzed? Standard answer. For those of you that hate electrolysis, you can get a mark here. Nice, good. Ions, somebody's put it in the chat. Ions not free to move. Good. Lovely. can't carry charge, not free to move. Name the product formed at the negative electrode when aqueous calcium. Oh, that's a bit hard for you, man, who haven't had the rules. So the rules of electrolysis. You need to remember these rules if you are given solutions. By the way, electrolysis has come up every single year and has been worth at least 10 marks, the whole question. So there hasn't been a year yet where electrolysis hasn't come up. So I would predict, what the genius this man in the hat is. I would predict that electrolysis is going to come up. And if it isn't, I'll be like, well, it's the first year it hasn't come up. So it's come up every year so far. Hasn't been a year without it. So there are rules to solutions. So solutions will have the symbol AQ, and there are some rules to these. So remember the rules of electrolysis, and the rules are as such. At the negative electrode, I'm just going to write that. I'm not going to use the word cathode or anode. You don't need to. So I'm just going to say at the negative electrode. Oh gosh, let's not write hydrogen. Let's keep it. We ain't got all night. Let's keep it short and sweet. H2 will, I could say, be discharged, or will be. I'm just going to say will be produced. So whenever you have a solution, hydrogen will be produced unless a less reactive metal is present. Then it's going to be the less reactive metal. Now, if you know your reactivity series, the only two metals below hydrogen in any sensible reactivity series are copper and silver. So the general rule is, if you have a solution, the metal is not being formed, only hydrogen, unless the electrolyte, the solution, contains copper or silver. So the general rule is it's hydrogen coming off. You can be pretty sure of that, unless copper is present, is the general rule. Now, at the positive electrode, at the plus electrode, a halogen always is produced. Do you guys know what a halogen is? It's a group 7 element. Fluorine, chlorine, iodine, bromine. What they're saying is, if it is present, it's always coming off, right? If chlorine is there, it's always coming off. Nothing's coming off instead. It's the halogen. Now, there is one time where it won't come off, and that's if there's no halogen. So at the plus electrode, if no group 7 halogen present, then oxygen is produced. Okay, so those are your rules of solutions. Solution, when they use the word solution, those are your rules. Hydrogen always comes off at the negative electrode because that's where the metals normally come off. The positive metals normally go there, but hydrogen goes there instead. You get bubbles of hydrogen gas. Unless copper's around, then it's copper and hydrogen stays in the solution. Halogens will come off if present at the positive electrode, chlorine, bromine, iodine. But if there is no halogen, like for instance, if it's sulfate, magnesium sulfate, sulfate is not a halogen, then oxygen will be made. Now, I'll go through more of that when we do the questions. So, name the product formed at the negative electrode when aqueous, this means it's about solutions, calcium chloride is formed. So, what do you reckon, folks? What's the answer to that? Calcium chloride, what's coming off at the negative? Calcium is positive ion, chlorine is negative. You will be forgiven for saying calcium because calcium's positive, it will be attracted to the negative. But you don't know your rules if you write that. The rule is at the negative electrode, hydrogen will always be produced unless copper is around. So we're going to say hydrogen. That is what is coming off, hydrogen, every time, unless it says copper is there. Okay, nice. Now, what is the half equation for the reaction at the positive electrode when aqueous calcium chloride solution is electrolyzed? So, chlorine a halogen is always produced, not a halide ion. The elemental halogen, Br2, I2, is made, so is on the product side. So I look down here and say, which one shows a halogen being made? because I know a halogen's present because it says chloride, which is group 7. So which one shows a halogen being made? Only this one. What does this show? That is an ion, not the chlorine. That's not chlorine, that's chloride ions. Chlorine will be made. That's showing oxygen being made, so that's not right. And this one is showing hydroxides being made, so that's not right. And that's not right because it shows chloride, so it's this one. Chlorine is made. Okay, we're going to go through some of these. Let me go through another solutions one. Let me not go through this one yet. Let me give you this solutions one. So, this question is about chemical reactions and electricity. Electrolysis and chemical cells both involve chemical reactions and electricity. Explain the difference between the processes in electrolysis and in a chemical cell. That's a triple question. That particular 2 marks of this question will not come up in combined, but the rest of this question applies to combined. All right, so stay with it if you're combined, because it's only this bit that you don't need to know about. So I'm going to give you the difference between electrolysis and chemical cells. They're 2 different things, only for triples. So in electrolysis, in fact, I'm not even going to put the positive and negative, but in electrolysis, so I'm going to rub out halfway, but I'm just going to give you, so in electrolysis, electrodes, I'm going to give you some things that are different. Electrodes are inert, meaning the electrodes do not react with the electrolyte. They're inert. They don't react. They're normally made of carbon or platinum, something quite unreactive. So in electrolysis, the electrodes are inert. Electrolysis produces, what does electrolysis produce? Electrolysis produces electricity. No, electrolysis produces elements, sorry. But also you could say electrolysis splits compounds. So that's my other difference. Electrolysis, the electrodes are inert. Electrodes splits a compound using electricity. I don't want to spend too long on this. What about a fuel cell? So with a fuel cell, a chemical cell, not a fuel cell, I'm talking out my backside, with a chemical cell, because it mentions chemical cell, you still have electrodes. So guess what? This year they might ask you the similarity between electrolysis and chemical cells. Both involve electrodes, both use electrolytes. That's where the similarity stops. So the difference with a chemical cell is electrodes are not inert. Electrodes react with the electrolyte. So they actually have a reaction with the electrolyte. Atoms from the electrode go into the electrolyte, and so they're reacting with it. And what else can we say? We can say electrodes are different materials. What do I mean by that? In electrolysis, both electrodes are made of carbon. In electrochemical cells, this might be zinc and this might be silver. We use different elements or different materials for each electrode. The electrodes must be different. They mustn't be the same in chemical cells. So there's a difference. The electrodes react with the electrolyte, and the electrodes are not inert. They are different. They're different as well. They're different metals. And the electrodes are both made of metal. Anyway, this produces voltage. This is a battery. It produces voltage. So you're not doing it to split a compound. You're doing it to produce voltage. Right, enough of my whiffle, waffle, waffle, because I could just be here waffling and waffling and wibbling, and that's no good. So let's zing on, right? Let's get on to the electrolysis business. A teacher demonstrates electrolysis of molten lead bromide. Molten means liquid, melted. Bromine is produced at the positive electrode. Complete the half equation for the production of bromine. You should balance the equation. So we've got Br minus. They're telling you production. Bromine is made. So bromine is a diatomic molecule, Br2, and you're going to get 2 electrons coming off. That is the equation for a halogen. Guess what? If it's chlorine, same thing. Going to go like this. Oh, shit. Excuse me. Going to go like that. If it was iodine, the halogens, chemistry is all about patterns. They're all going to react in the same way, the halogens, okay? The halide ions, group 7. So, whoa. Oh, let's just leave that there. Let's leave that there. Let's leave that there. So I'll start flopping about. Now, here comes the rules. Here comes the rule bit I was talking about. So, here's the rule bit. Complete table 4 to show the amount product at each electrode. We've got to bust those rules. Do you remember I went over the rules? So I'm just going to remind you of the rules, and then you guys are going to tell me what's coming off. So just a quick reminder on the rules. The rules are solution rules, not molten rules. In solutions, you have H plus and OH minus ions, and that means we don't get always the things we think coming off. So at the negative electrode, it's going to be hydrogen unless copper is present. At the positive electrode, it's always going to be a halogen if a group 7 element or ion is present. At the positive electrode, if there is no group 7 element or halogen halide ion present, then we're going to get oxygen. Let's go back and see if we can apply those rules. And here we go. 2 aqueous solutions. So we know we're dealing with solutions, because we see that AQ are electrolyzed using inert electrodes, unreactive that means. Show the product to each electrode. So I've got copper nitrate. What is coming off? If I have copper nitrate, what's coming off at the positive electrode? They've told me copper's coming off at the negative. Am I going to write nitrate? What am I going to write? Product at the positive electrode is always going to be a halogen if present. Is there a halogen there? There's no halogen, so the answer is oxygen. Whenever there's no group 7, it will be oxygen. Now we look here and we go down to this one and we go product at the negative electrode. Is there a more reactive metal? Yes. The only time copper comes off in a solution, the only time a metal comes off is if you have copper, so it's hydrogen coming off here. Potassium's too reactive, it stays in the solution. And then iodine, yes, that's a group 7, so we're going to have iodine form. Don't write iodide, write iodine. That's the element. So that's how you apply the rules to the solutions for electrolysis. What are we doing next? Which is the correct half equation for the production of sodium? Again, look for the cheat code. Production of sodium. Which of these shows sodium being made? Well, not that. That's a sodium ion. Well, not that. That's a sodium ion and an electron. Ions are not the same as the element sodium. That is the only one that shows sodium being made. And just on that, folks, let me get rid of that. Let me go through the half equations for you for this. So where are we? Oh my days. It's late, you know, it's probably time to get to bed. But if it, yeah, what? Let's go. Right. You don't want to be burnt out for your exams. So half equations for metals are the dead easiest thing. If a metal's coming off, so imagine it's copper coming off. In electrolysis, it's different than redox half equations because you're starting with an ion. So copper's like this, and then copper is going to pick up 2 electrons and it's going to become copper atoms. And guess what? This oil rig, this is reduction, because reduction is gain of electrons. So if someone said to me, why does copper come off? I should say, why is copper produced? But I've said does now, so I've kind of screwed it. Why does copper come off at the negative electrode? And that could be worth 4 marks. I know what you're saying. What the arse? How can that be worth 4 marks? What we want to say is Cu2 plus is positive, attracted to negative electrode, right? positive, negative attract. And then we want to mention oil rig. So we're going to say it is reduced. It gains electrons. And so you're saying all this wonderful information, and then if you're really smart, you're going to bust out the half equation because they love that as well. So it gains 2 electrons to become copper. So that will get you loads of marks, and you can. It's the same. It doesn't matter if that is aluminium. It doesn't matter what metal that is. You just got to balance the plus with the electrons. And in electrolysis, the electrons are the metal ions are gaining electrons. Okay. Now the hardest one, there's no rule, Sophia, for molten electrolysis. So I'll go through molten in a second, because with molten electrolysis, see the thing with, and this is a question they ask as well, the reason we have rules for solutions is because with solutions you get something like sodium. The most common one is sodium chloride, AQ, right? AQ, what is AQ? AQ is water, and water contains H plus and OH minus ions. So the problem is sodium's in group 1 is Na plus and chlorine is minus. Only one can be the champion. Only one. Now it's kind of argument, is it the champion that comes off or is it the loser that comes off? Well, hydrogen will always go to the negative electrode unless copper ions are present. So this sodium ion, if it was molten, if I was molten, that would be an L for liquid, and there would be no H or OH minus. So it's dead easy when it's molten. When it's molten, it's just going to be, okay, sodium ions come off at the negative electrode. And what happens? They gain electrons, they are reduced and they become sodium. And chloride ions, they go to the positive electrode, and we always draw the electrons on the right at the positive electrode, and it's oxidation. So they're going to be Cl2. Most non-metals are diatomic like that, and then you're going to get 2E minus. Now, if they're AQ, you have the issue with AQ is that you have hydroxide and hydrogen ions. So a battle takes place between the positive and the positive ions and the negative ions. There's like choice of 2. So AQ solution means we have to bust the rules. So in this situation, sodium is too reactive to come off. Sodium stays behind in the solution like that, and the hydrogen ions go to the negative electrode, and H plus ions become H2, and then we can write the equation for that if we wanted, and the equation for that would be 2H plus 2E minus goes to H2. And then if we look at the positive electrode, we would say, is a halogen present? Yes, Cl minus is present. So OH minus is going to stay behind, and the chloride ion is going to come off and form chlorine gas, and then we can write the equation for that. So that's how you apply the rules. Now they could ask you, what gets left behind? Well, that is sodium hydroxide, which if they tested it with universal indicator, just like when we do alkali metals, that would be purple. It would have a pH of like 13 because it's a hydroxide. So that's when you apply the rules. And the rules, obviously electrolysis is a very hard topic, so don't beat yourself up if you come out of electrolysis with 50% of the marks, because it's going to be like a 10-mark question. If you get 5-6 marks of electrolysis, you've smashed it, because you're going to get more marks on the easier topics. So and not all of electrolysis is half equations. Look, this is only worth 1 mark, this half equation over here, so you don't need to worry. Now the hardest bit of electrolysis is when this happens. So let me show you the hardest equation in electrolysis to deal with is this. So when there are no halogens and we use the group 7 rule, we go, there's no group 7. So what's coming off? Well, we make the ions. Now, you're supposed to know off by heart that SO4 is 2 minus, and that will then tell you that copper must be 2 plus, so Cu2 plus, And then water, AQ, always has hydrogen ions, which are acid, and hydroxide ions, which are base. By the way, they cancel out to make H2O, so neutral. Anywho, what's going to come off? We use the rules. So for copper sulfate, what two things will come off? An electrolyte, good question, is a solution containing ions that conducts electricity. It's not a solution, sorry. It's a liquid because you can have molten. So it's a liquid that conducts electricity. So a liquid that conducts electricity. So it could be molten or it could be aqueous. That is an electrolyte. Now here we would use the rules. I'm going to get off electrolysis in a sec, folks. We could use the rules, and the rules here would be there is no halogen present, so oxygen's going to be made. And I want to show you the disgusting equation of how oxygen's made. First of all, copper is less reactive than hydrogen, so it'll be copper that comes off this time, and it will be that one. Easy peasy. But here's the horriblest, nastiest half equation in the history of electrolysis, and this has come up before, and it's worth 3 to 4 marks when this comes up. So when there is no chloride or bromide or iodide or fluoride, there's no group 7 and it's AQ, then OH minus goes to the positive electrode, and OH minus becomes H2O, oxygen gas, because we remember that it's oxygen gas that comes off, and it gives away electrons, so it's being oxidized and it is forming water, oxygen and electrons. And the balance of this is 4OH minus goes to 2H2O plus oxygen plus 4 electrons. And that is what happens when there's no halogen there. That is the half equation for that one. Right, what I want to do, guys, is do one last thing on electrolysis, then I'm done with that. I just want to give you a quick question on aluminium. No. Here we go. You do have to know about the electrolysis of molten aluminium oxide, not solution, not AQ, molten aluminium oxide. Aluminium is produced by electrolyzing a molten mixture of aluminium oxide with cryolite. Now, aluminium is higher in the reactivity series than carbon, so it can't be extracted by normal means. We only discovered it in the last 150 years, once we discovered electricity and started using electricity, and we started doing electrolysis. So aluminium is produced by melting aluminium oxide with cryolite. Explain why a mixture is used as the electrolyte instead of just using aluminium oxide. So what does cryolite do? Does anyone know what cryolite does? Cryolite lowers the melting point, so it acts as a catalyst. So cryolite lowers the melting point, so you use less energy to melt Al2O3. Okay, it's a catalyst, cryolite, and it lowers the melting point. You're going to use less energy to melt the aluminium oxide. If you use aluminium oxide only, it will cost you a lot more money. You'll use a lot more electricity. Now, here's the problem with aluminium oxide and the electrolysis of aluminium oxide. And this is in the electrolysis of aluminium oxide uses carbon electrodes, which they always use. And the carbon electrodes, have to be replaced. So do you know, by the way, this looks a bit weird because they use the base of the container as the negative electrode. And that's kind of cool because remember, this mixture is molten, so it's only really containing Al. I know it's got cryolite in there, but it has Al3 plus that become Al, and then it has O2 minus ions that go here and become oxygen. Why do we need to replace the electrodes? So as the anode is made of carbon, that is right, carbon plus oxygen makes carbon dioxide. So the electrodes, I don't know, we could say wear away or erode. Now, I could go in and explain that. The electrodes are made of graphite or carbon atoms. Oxygen is produced at the positive electrode. It reacts to form carbon dioxide and wears away the electrodes. Now, what happens at the negative electrode? What reaction is going on here with Al3 plus to aluminium? Does aluminium gain electrons, lose electrons? Aluminium ions gain electrons, aluminium ions lose electrons. What happens there? This is in combined higher as well, yes. So it is reduction. Yeah, it does gain electrons. But is it ions or atoms? No, it gains electrons, aluminium. But are they ions or atoms? Thank you, that's right. Aluminium ions. No, no, it's aluminium ions gain electrons. So what happens is Al3 plus picks up 3 electrons and becomes Al. We want to make atoms of aluminium, so we give the ions electrons and they go back to being aluminium atoms. Complete the balanced half equation for the process at the positive. This is just saying this. So we've got O2 minus, and the O2 minus ions go here and become O2, and they give away electrons. And then we just need to balance it. So to balance this, I have 2 oxygen atoms there. So I'm going to need 2 oxygen ions. But that means 2 times minus 2 is 4 electrons. So that is a bit disgusting, because we need 4 minuses, right? Because you've got 2 times 2 minus. Okay, it's 4e minus. To be honest, I'm feeling like wrapping up the stream now. You know, you guys need to get some sleep. It's late. So, yeah, aluminium. Okay, so aluminium ions gain electrons because aluminium ions are positive. So they're attracted to the negative electrode, and they take 3 electrons because they're plus 3 ions. So they gain 3 electrons, and we call this reduction. Oil rig. Reduction is gain of electrons. So if I have to explain, if someone said to me, and they could give you this 3 marker, maybe 4 marker, why is aluminium produced at the negative electrode? I would say aluminium ions gain electrons. They are reduced because they gain electrons. That's going to be a mark. Aluminium ions are positive, so they are attracted to the negative electrode. They pick up electrons there and are reduced to aluminium. We'll go through a titration and then we'll finish up, people, because you need to get some sleep. Honestly, it's one of them. So let me zing through how to do the old titration. Now there's 2 elements to the titration that could come up, and by the way, titrations are only triples, so I'll quickly zing through titrations. By the way, I have a live which I did a couple of weeks ago on titrations, which is going to be a lot better than this explanation that I did. But what we have with a titration, and this is triple only, you have a burette like this. I've actually got lives on all of this stuff. I've got lives on all of the different bits that I did in the last couple of weeks, and they were 1 hour each, and specifically like on the history of the atom, on electrolysis, on titrations. What the arse? Why is that not turning? This wants to be a bum. Okay, it just wants to be a brute. So when you carry out a titration, you need to know what this bit of equipment is called, and this is called a burette. Don't beat me up over my spelling, because I ain't got the kind of energy to be checking that. And then you got a little tap on the burette. Now you're going to get a conical flask, and your conical flask you're going to place on top of a white tile. Sometimes that's a nice mark. I will go through the calculation for this, but I'm going to go through the 6 mark explanation to the practical first. So why do we do titrations? We do it to find the concentration of an unknown acid or alkali if you're triple. And what you're going to do, you're going to put your unknown. I always put the unknown in there, but it doesn't really matter which one you do. So you're going to transfer to here 25 centimeters. You normally use transfer, and this is key, 25 centimeter cubed. of, I don't know, I'm going to say alkali, unknown that's my one of unknown concentration. I'm going to transfer that, and here's the key: using a pipette. Now, a pipette is the most accurate way to transfer a volume. It's more accurate than a measuring cylinder. It can transfer exactly 25, and you don't have to worry about the meniscus, the bend of the liquid in your eye level. You don't need to, oh, do it at eye level. You don't need to say that with a pipette. The pipette is, it looks like this. It's like a long glass thing like that, or plastic thing like that, and you suck up all the liquid. Anyway, you're going to transfer 25 centimeters in there. Generally it's 25. You're then going to, so that would be my number one, transfer 25 centimeters of either the acid or the alkali there. Then it doesn't matter if it's the unknown or the one you know about, just transfer 25 there using a pipette, and that's your first point. Next one, add a drop, let's put a few, meaning two, add a few drops of indicator to conical flask. So what this is going to do, if you use phenolphthalein, this is going to change this and make it go pink. In alkali it's pink, it's colorless. In acid, phenolphthalein. Then what I'm going to do is number 3, I'm going to add add acid to burette. Now what you need to do is you don't want your eyes below the burette. So when you're adding the acid, safety, your eyes need to be above the burette when you add the acid. So add acid to burette, wear goggles, and you should be, don't do that at eye level in case you spill acid in your eye. You don't want that to happen, or on your head. So we're filling the acid or below like that. We fill it right up the burette to the top, so you don't need to worry. Add acid to the burette, wear goggles, whatever, bloody blah, bloody blee. Now what you're going to do, you're going to, number 4, you're going to add acid. You can do a rough titration first. I'll talk about that after. Add acid drop by drop to conical flask. And ideally, you should swirl the conical flask. This is why we don't use a beaker, because if I swirl a beaker, all the liquid comes out on my hand. The conical flask is shaped like that, so you can do that with it without any of it spilling. So swirl conical flask after each drop. And then you want to stop when color changes. Now, I've run out of room. I should use the word permanent. Stop when it is a permanent color change. What do I mean by that? If it's pink and I add a drop of acid, it might go colorless and I think the reaction's done, and I walk away and the pink color comes back. So you want to add a drop, swirl, wait. Add a drop, swirl, wait, and see if it's permanent color change. When it doesn't come back, that's when you stop. You look at your burette and you record the volume you have added. So you're going to record the volume of acid you've added from the burette to the alkali, and you'll record that. That's called a titra. Now you can always mention for extra marks things like use a white tile. Why? It makes the color change easier to see. Now, there is a more accurate way to do this using a colorimeter, which is a light detector, and you shine light through and it measures the absorbance. And you could do that because human eyes, it's subjective. You might tell me it's gone colorless, and I might say, no, I think it's still slightly pink. So it's down to the subject. So it's not super accurate. Well, it is accurate because pink to colorless is pretty obvious, but yeah. Anywho, right. What else do we need to talk about? You're going to repeat that 3 times. You're going to repeat it 3 times until you get concordant results. I've kind of run out of room there, but I would repeat 3 times, get concordant results. Concordant results. That means they're like within, depends on your example, but within 0.1 of each other. And repeat 3 times, get concordant results, and then calculate a mean titra. If you have any non-concordant results, you do not include them in your mean. So if I have 3 results like this, 22.5, 22.6, 23.2. I am not including that in my average, and only these two are concordant. They're within 0.1 of each other, so I'm going to include those. It'll probably be to 4 places, so it'll be like that. So 22.55, 22.60, I'll go yes, they're concordant, I'll use those. I won't use 23.20, that's not concordant. Okay, any questions? No, you don't need to know specific years for the history of the atom. Oh, I did a bit of that earlier, the bonding of carbon. Now, there is an equation you need to do for this, and I'll go through that with you now. So I'll go through the equation, and then I'm out of here, peeps. So N over C times V, we're going to use that. I'm just going to quickly go through the calculation you would do for this. So bear with me, and then I'm out of here. Because I haven't covered everything, but you know, that's life. We're zinging now. Here we go. Right, so there are some other things with the titration. You could spend ages talking about titrations. Right. So why do we do titrations? We do titrations to find out the concentration of an unknown. And so what I'm going to say is here is my calculation, and this will be like 4 or 5 marks. They may include it with the write-up. They might give you the data with the write-up with the 6 marker, but often they're separate. Sometimes they're 5 marks. So a student titrates an unknown concentration of NaOH. I mean, they would say like the student adds 25 centimeter cubed of NaOH via a pipette to a conical flask, an unknown concentration of NaOH. Let's just zing that, right? Let's get rid of the story. We don't need the story, people. I can't be bothered to write a story. It's too late for that. So essentially, I'm going to tell you, these are the facts you're looking for. Unknown conc. We've got 25 centimeter cubed of NaOH. This is probably, although not always, going to be in my conical flask. And then they're saying, look, they titrated, what you titrate is in the burette. So that's what you titrate. You've got a little tap there. They titrated 20, they found the mean titer was 22.50 centimeter cubed of HCl. And then they're going to say like HCl of 0.5 mole dm cubed. Calculate the concentration of NaOH. And all we're going to do here is go, right, well, I got that, so I'm going to straight away say, what have I been given? Well, I've been given a volume, and I've been given conc. This is obvious. I'm going to use N over C times V, so I am going to go 22.50. I'm going to divide that by 1,000 because we have to use decimeters, and so that is going to be 0.0250, whatever, or 0.0225, and I'm going to times that by 0.5, and that is going to give me, oh my good gosh, 0.0225 times 0.5 equals 0.01125. So that means, what have I done? And a lot of people are like, what the hell have we done so far? So we've got 0.01125, and that was of HCl. So that is moles, N stands for number of moles, of hydrochloric acid. So I've worked out my acid. I now need to use the equation that they will most likely give you. Now the equation would be like this: NaOH plus HCl. With titrations, you're only interested in the reactants and the coefficients of the reactants. But that would make sodium chloride plus water, because it's salt. Base plus acid makes salt and water. And it's going to be a 1-to-1, right? Yeah, it's going to be 1-to-1. So that's nice and easy for us, 1 to 1. So that means if I have that, I also, whoopsie, have that of NaOH. Now, if it was sulfuric acid or magnesium hydroxide, it would change the amounts of OHs and Hs, so it might not be 1 to 1. I mean, a quick cheat code, you can tell this is going to be 1 to 1 because I've got 1 OH with 1 H to make 1 water, and that is neutralized on a 1 to 1 because you're making 1 water. Anywho, now we know the moles of sodium hydroxide. All I got to do is bust that with that and N over CV. So I'm going to go 0.01125 and I'm going to divide that by 25 centimeters. Don't forget you have to use decimeters, so I'm going to divide that by 0.025. And if I divide that by 0.025, I know you work that out by dividing by 1,000, I'm going to get my concentration of sodium hydroxide was 0.45 mole dm to the 3. Okay, now yeah, good luck people. So yeah, now something they throw in occasionally. So we worked out, by the way, that'll get you like 4 marks. We worked out it's 0.45 moles per decimeter. Something they throw in occasionally is convert this into grams per decimeter. How do we convert that into grams per decimeter? Well, guess what? AQA are so beautiful that they will give you a big fat clue. And they will give you the ARs in the question. The atomic masses in the question. What the arse is going on here? Hold on. They're going to give you a clue in the exam. Hold on. What the flibber-libber-loober? So they want grams per decimeter. So what we're going to do, we're going to use, I'm running out of room massively, mass over mR times moles. And all you're going to do, if you know that's 0.45 moles, that means N equals 0.45. Why? Because it's 0.45 per decimeter. So all I'm going to do is N times the NR. What were we working out? We were working out NaOH. So I'm going to go 23 plus 16 plus 1 is 40. So I'm going to do that times the MR of 40. And that will give me the grammage. Is that right? What is the mass? 23, yeah, for sodium. 16 for oxygen is 39. And 1 for hydrogen is 40. Okay, just seemed a bit easy, that, the old 40. It's that kind of time of night as well. So that would equal 18 grams per decimeter. So if they ask you to convert, they will give, and the clue that you would have to do the MR is they would give you the AR. They'll give you Na equals 23, O equals 16, H equals 1. Bosh. Anywho, listen, I am smashed. I think you guys should go and chill out. Another question, another one. Let's have a look. Explain why steel is harder than iron. 5, 4, 3, 2, 1. 3 marks. Why is steel harder than iron? Steel is an alloy. Boom! Steel has different sized elements. Boom! Disrupts the layers. Boom! The layers can't slide. Boom! Great. You're all over it. Oh! It's diamond, people! People in the comments have been saying diamond. Why does diamond have a high melting point? It's a non-metal. It's covalent. What kind of structure does it have? Is it simple? Is it giant? Diamond has a giant structure. Lots of strong covalent bonds. Require lots of energy to break. Boom! We smashed the marks. So, anytime something has a cheat code, if you get confused with ionic, metallic, covalent, if something has a high melting point, it has to be giant. Forget whether it's covalent, metallic or ionic. If you lose that mark, boo-hoo. But you can gain a mark. The moment something has a high melting point, it is giant structure. So Diamond has a giant structure. Yeah, great if you can remember it's covalent. It has a giant covalent structure. That means it requires lots of energy to break the strong bonds, and hence the high melting point. Now, if they said, why does copper have a high melting point? Copper has a giant structure, but this time copper is a metal, it's metallic. And then I can say lots of energy needed to break the strong metallic bonds. There we go. Lots of strong metallic bonds need lots of energy to break. Now, if it was sodium chloride, we would say it has a giant ionic structure. Lots of energy needed to break the strong ionic bonds. Now, yes, if you know the definition of ionic, metallic and covalent, you can add in electrostatic force of attraction between shared electrons and nuclei, or between, in metallic, delocalized electrons and positive ions, or in ionic, between positive and negative oppositely charged ions. But why do that when you can pick up 2 marks just from giant structure and lots of energy needed to break the bonds? Now, carbon, each atom is bonded to 4 others. It has no free electrons. It cannot conduct electricity because all the electrons are locked into covalent bonds, so it does not conduct electricity. But the answer as to why it's hard, one of the hardest substances, why it's used in drill bits, the edge of swords, knives, whatever, DJs' decks, their needles on their decks, is because it is the giant covalent structure. Lots of strong bonds need lots of energy to break. Graphite's a form of carbon. Explain why graphite conducts electricity. What can we say, peeps? It has delocalized electrons that carry charge through the structure. Now, why? They're the 2 marks. Third mark, why does it have delocalized electrons? Uniquely for graphite, don't say this for metals, but for graphite, each carbon is only bonded to 3 others, unlike diamond, which each one is bonded to 4, so there's no spare electrons. Remember, carbon's in group 4. It has 4 electrons in the outer shell. In graphite, only 3 are being used, so the 4th one is spare, is free, is delocalized, and can carry charge. In diamond, all 4 outer shell electrons are bonded. There are no spares, so it cannot carry charge. Right. Why can sodium chloride conduct electricity? Right, well, sodium chloride can't when it's solid. You have to melt it or dissolve it. You make it aqueous or you melt it so the ions are free to move and carry charge. So hopefully you know that. What else? Why does sodium metal conduct electricity? Sodium metal has delocalized electrons and positive metal ions. The delocalized metal ion, the delocalized electrons can carry charge. What do we want to do? We want to do. Okay. This one is super hard. I don't think I want to explain that. Redox reactions. Okay, anytime you see this, because I want to just focus on, here we go. Anytime you see this, Paul, low. Boiling points are low. If I see the word low melting point, low boiling point, what my brain is going to say, if you have a low melting point and a low boiling point, you are a simple molecule. Simple molecules are always covalent. They're non-metals. I know you're saying, well, sir, diamond's covalent. That's a giant covalent. Most covalent molecules are simple molecules. If you have a low melting point, a low boiling point, or you are a gas, chlorine, bromine, nitrogen, oxygen, hydrogen, carbon dioxide, sulfur dioxide, methane, any gas in the periodic table or any compound that is a gas in the room with you right now or anywhere on the earth is a simple molecule. That's why it's a gas. And all we need to say is simple molecule, weak forces between the molecules. You can say weak intermolecular forces if you want. Weak forces between molecules, not a lot of energy needed to break. So not a lot of energy needed to break, whatever. Yeah, easy to break, easy to overcome. That comes up all the time. Bish bash bosh, already done one of them, not doing that again. I will go to, 1 second. Someone said they want another titration. What am I on? What is this? This is Ask the Teacher business. Okay. That is all of that. Let me go here and just zing. I'm going to sleep soon. Oh, redox. You want me to go through the redox one? Okay, I'll go through the redox one. But it's like, At this stage of the night, you've got to say to yourself, sometimes you just got to write stuff off. It's called tactical, being tactical, yeah? You're going to lose certain battles. You want to win the war, you're going to have to lose certain battles. You can't try and win every battle when you end up just like flopping. So you've got to be technical and tactical, like 3 marks. Anywho, look, so if I'm tactical here, explain which species is reduced between magnesium and iron chloride. What do we know? We know oil rig. And you guys should know oxidation is loss of electrons, reduction is gain of electrons. So if I'm going to guess what is reduced, oh no, it says explain which species is reduced. I definitely know I can get one of those 3 marks by saying because it gains electrons. Because I know from oil rig. So this is exam technique. You're baffled. You're like, I ain't got a clue. But if you come out with 1 out of 3, you've actually done pretty well. So you've remembered that reduction is gain of electrons. So what's gaining electrons? Well, let's check out magnesium. Magnesium is in group 2. It has 2 electrons in the outer shell. Over here, magnesium's in an ionic compound, so magnesium is going to be Mg2+. Has it gained or lost electrons? It's lost electrons. It's lost 2 electrons. Magnesium has been oxidized, so I know it ain't the magnesium that has been reduced. The magnesium has lost electrons and been oxidized. Let's check out iron here. Iron is with chlorine. What do you think the charge on iron is? If you have FeCl3, chlorine is in group 7, is always Cl-. If I have 3 Cl-, oh my good gosh. If I have 3 Cl-, then my Fe must be 3+. Right? We're cool with that. Oh my god, where's my pen gone? What's going on? Right, so let me get rid of that. So I know Fe is 3+. Then I want to say, oh, but what is Fe afterwards? Well, Fe's on its own. It's back to being an element. It has neither lost or gained, like it's an element now. It's back to its original form. So what's happened is it's gone from 3+ to Fe. So how did it go from 3+ to Fe? Guess what? It gained 3 electrons. And that is how it did that. So where are we? So the equation they're looking for is that in the mark scheme. They're looking for Fe3 plus 3E minus goes to Fe. And that is reduction, because reduction is gain of electrons. So you may even get 2 marks from saying iron is reduced, it gains electrons. Okay, half equation is the 3rd mark. So what I'm saying is, even if that is uber hard, that is like the higher level stuff, like yeah, you get the idea. Okay. Close, dude, close. But remember, it gained electrons. Reduction, the electrons are always on the left. They came up with oil rig, but I don't think that really helps. You need something to remember that reduction is gain, electrons on the left of the equation. Oxidation is losing, so the electrons are on the far side. They're on the right when you write an oxidation equation. Okay. No, I'm not doing that. Oh, you said, someone said they want me to do a titration question. I'll quickly bust out a maths titration one. Let's go here. Why am I talking like a dipstick? Okay. Oh, geez Louise, mate. Limiting reactants. That's limiting reactants. What's this? This is concentrations. So for this one, see, I'm gonna get myself distracted. For this one, you're gonna do mass over conc times volume. You have to know this equation as well for these dirty ones. Right, you got 300 grams per decimeter. That's a conc. In 1 decimeter of water. The student used 50 centimeters. That's a volume cubed. In each experiment, calculate the mass of copper chloride used in each experiment. So we know the conc is that. So the conc is 300. and I want to times the conc C times V, so I want to times that by V. The volume is 50, but you're not allowed to just bust out 50. You've got to divide it by 1,000 because we use it decimeters. So we want to do 300 times 50 over 1,000. What's 50 over 1,000? 0.05. So 300 times 0.05. Is that right? I don't know if I've done that right. Oh my good gosh. Have I done that right? I think so. Yeah. Well, whatever. 15 grams. I guess we can check because I can do 15 over that should give me 15 over the volume. So should give me 300. So if I go 15, which is the mass, divide it by my volume. What did I say the volume was? 0.05, and that equals 300. Yeah. So you can reverse it and check your calculation. Anywho, let's zing on. This is combined. This one combined higher, if you was asking. But triple is triple dipple is what do you call it? Yeah. Oh, that's a reacting mass one. Most of these are combined. Some are triple. Make sure you watch out for this. Watch out for this one. This is the pH one. It's only a couple of marks, but pH 3. What have we? How many times weaker? How many times weaker have I made it? I've gone from 10 to 1,000. That's 100 times weaker. Each pH is a factor of 10. So I've gone from pH 3 to pH 5. So I've made it weaker by diluting it by 100 times, which is 10 times 10. Each factor of 10 is worth 1 pH. The higher the pH, the more dilute the hydrogen ion concentration is. Okay, so the value of X is 5 there. If it was the other way around, if I said I've got pH 2 and like we go, oh yeah, whatever, yeah, I'm not going to bother. Yeah, if we have pH 7 and I go 10,000 times stronger, if I have pH 7, I make it 10,000 times more acid or 10,000 times stronger. That is a factor of 10 times 10 times 10. So I've dropped 3 pHs and gone pH 6, pH 5, pH 4. So, yeah. What we're looking for is a titration. So stop whiffle waffling, you idiot, and find a titration. Got enough of these questions up here. Look, there's another pH one, guys. So a solution of hydrochloric acid had a hydrogen ion concentration of 1 mole. The water was added to the hydrochloric acid until the pH increased by 1. Okay, so they're diluting it. So maybe it went 5 to 6 pH. So they're basically saying it like went pH 5 to pH 6. It got diluted. What was the hydrogen ion concentration of the hydrochloric acid after water had been added? So it was 1 mole, and then we got 10 times weaker. What is 10 times weaker? Divide that by 10. It's going to be 0.1 mole per decimeter. So it got 10 times weaker. So that is going to be the answer there. Okay, that's quite tricky, but that's another one of them conks. That's like Avogadro's. Oh my days, man. Where's the titration? There's a titration. Oh, watch out for this one. Just a quick reminder for you peeps. If you're asked to measure uncertainty, so if you're asked to measure the uncertainty, and this can be in combined and triple, you have something called uncertainty. So uncertainty, what is it equal to? It's equal to the range divided by 2. So what we're going to do is the range. We take the lowest, which is 6, the highest, which is 11. I go 11 minus 6 equals 5. I divide it by 2 and I get 2.5. But sir, none of these say 2.5. But 2.5, as you know in maths, is you're going to round that to 3. So the correct uncertainty is 3 centimeter cubed here. So you do the range, divide it by 2, and in this case we had to round to 3 rather than drop to 2 because it was a 5. If it was 2.4, we'd have put it as 2. Okay, no. Where are you, titration? Maybe I don't have a titration here. I don't think I've got a titration question. I'm going to have to bust one up for you. Yeah, that's a limiting reactants one. All right. Oh, limiting reactant. Limiting reactant is here. This is like a limiting one. Calculate the maximum mass of copper produced in grams. You should determine the limiting reactant. Let me show you then for this one. So, it's a little bit of a bummer. Look, they've told you have 108 grams of aluminium and it reacts with 1.2 kilograms of copper chloride to produce copper. Blah, blah, blah. We've got the equation. So they've even given us the MRs. They're beautiful people. Beautiful. Great people. Okay, no need for Donald. 108 of aluminium. So what I'm going to do is I'm going to work out my moles of aluminium. So you're just going to go 108. We're going to divide the 108 grams by 27. And that's going to give me how many moles of aluminium I've got. So 108 divided by 27. And that gives me, I have 4 moles of aluminium. We have 4 moles of the aluminium. Now what I want to do is look at the ratio and say, okay, that's how many moles of aluminium. How many moles of CuCl2 do I need? So that's what I want to work out next. Is I've worked out how much aluminium we actually have. I'm not interested in this 1.2 of copper yet. I'm going to work out how many I should have. So we now go to the coefficients, and you'll notice there's a big fat 2 in front of the Al, and there's a big fat 3 in front of the CuCl2. So the ratio is 2 to 3. So as the ratio is 2 to 3, I'm going to take 4, and I'm going to multiply 4 by 3 over 2, or I can, some people prefer this, divide by 2 times by 3. Same thing as times in by 3 over 2. So let's do that. And what we're going to find, if we go 4 divided by 2 times by 3, 4 divided by 2 times by 3, we're going to get 6. So, I need 6 moles of copper chloride. So we need 6 moles of copper chloride, people. But do we have 6 moles of copper chloride? If we don't have 6 moles of copper chloride, then copper chloride is the limiting reactant. It's the one we don't have enough of. If we have more than 6 moles of copper chloride, then aluminium's going to run out first. Because what they're telling me is that 4 lots of aluminium will react with 6 lots of the copper chloride. And what I want to know is, I have 4 lots of aluminium. I need 6 lots of copper chloride. It's too late. I'm going bonkers. It's great. It's great. Nobody knows more about limiting reactants than I do. Nobody. Not even the professor. Okay, let's go. What we want to do here is... Oh my good gosh, I've lost my train of thought. Now we want to count how much copper do we actually have. How much copper chloride do we actually have? Do we have 6 or not? Well, what we're going to do, we don't want to use kilograms, so we're going to change that to 1,210 grams, because with moles we use grams. I'm going to divide that by the MR of copper chloride, which is 134.5, and we're going to find out how many moles we got, peeps. So we got 1,210 divided by 134.5, and that is going to give me 8.99 and 99 and 999. So that's going to give me 8.99 moles of CuCl2. Is that bigger than 6? This is excess. This is limiting. So I don't have enough of that. That's going to run out, and I'm going to be left with 8.99 minus 6. I'm going to be left with 2.99 moles of copper chloride left over. So I know that copper chloride's excess. I know aluminium is now limiting. So when you're given the 2 masses, work out the mass of either one, convert it to moles, use the ratio to find out you should have, and then go back and work out the other reactant and see, did you have enough to make the should have bit. This is the should have. what we would need in theory, and this is how much we actually have. And so that is in excess. Now it did say, calculate the maximum mass of copper produced. Here is the next bit that is a big, if you want to get all 6 marks, what is wrong with this, man? This pen is like, it's dying, and so am I. Here we go. Right. They're asking us how much copper is actually produced. Do I use aluminium? Or do I use this? Well, I can't use that there, can I? I can't use the copper chloride. Well, I can if I use 6. But the 8.99, 2.99 is left over. So I would recommend always when you're using, when you're trying to find a product, how much product you've made, always use the limiting reactant, because that is the maximum amount of products we can use. It's limited by that. So it's like if you're making cookies and all your cookies have to have a certain amount of chocolate chips, and you run out of chocolate chips and you still got dough and flour left over, then you use your calculation on the chocolate chips to how many cookies you can make. So the limiting reactant is like the minimum we can make, so the maximum we can make. So this has a ratio again of 2 to 3. Look, check it out, peeps. 2 to 3. So it would be the same thing. The maximum copper chloride I can make is 6, and I could have done it from the copper chloride because that was 6, and it's 3 to 3, 1 to 1, the copper chloride with the copper. So I know the minimum, the maximum moles of copper I can make. So we can make 6 moles of copper, and now it wants the mass of copper, the maximum mass of copper in grams. So what I'm going to do, I know it's 6 moles of copper, so I'm just going to do this equation, which is Mr times moles gives me mass. Mass equals Mr moles, whatever, and it's 63.5. So I'm going to go 6 times 63.5, and that is going to give me 6 times 63.5. Oh, Sugar Ray Leonard. 6 times 63.5. I forgot the point. 381 grams of copper. It's getting late. I wouldn't be surprised if that was completely wrong. But it should be right. Oh, I've got the answers here. I don't normally bother with the answers, getting the answers, but I've actually got the answers. Let's just double check. Yeah, it is right. It is right. It is right. Look, there you go. 381 grams. Bish, bash, bosh. They probably did it in a different way than I do, though, but there we go. Right. I'm so tired. Oh, Michelle, why did I use 6 of copper? How did I know it was 6 of copper? So, yeah, I didn't really, I sped through that bit of it. So, how do I know to use 6 of copper? I used the 4 of the aluminium, but look, the ratio, exactly the same as our ratio of aluminium to copper chloride. Remember, that was 2 to 3, so was 4 to 6. If this is 2 to 3, the ratio, and this is 4, then that is going to be 6. And you do that by going 4 divided by 2 times 3, or some people like to go 4 times 3 over 2, and that gives you 6. So because of the ratio of aluminium, my limiting to that, I know it's going to give me 6 copper is the maximum I could make when the aluminium runs out. But I could have also said, well, the aluminium will react with 6 moles of copper chloride, and they're in a 1-to-1 relationship. So that's another way of working out that it was 6. You wouldn't use the excess. Just don't use the one that's in excess to do it. I think it is time to wrap it up. Brrr. All right, I think we're going to wrap it up there because I've got to get to sleep, people. I've got to drop my kids off at school tomorrow. Listen, you guys have got to get to sleep. You could be all night, and I could just go on for days doing this. But, you know, it's late. So, just do the best you can. That's all you can do. And then take your knowledge forward on where you need to improve your revision. Because the tools are out there. There's 1,000,001 people doing walkthroughs and online on YouTube. And you've got teachers in your school that will help you after school and all of that, and lunch club and all of that. Just take forward what worked in the last few weeks of panic, what might have actually worked. You might be feeling like, oh man, I should have done this. I should have worked a bit harder throughout the year. You can't change that now, but what you can do is change it going forward. So you can't beat yourself up, but you can only, like, you know, what do they say? Make a mistake once, whatever. Make it twice, make it 3 times, and you're a bozo. So don't be a bozo. If you flopped on some of your GCSEs through lack of work, make sure you switch it round. All right. Good luck, people. Good luck. Good luck. You know, you think this is bad? You should try and handle A levels. A levels are sick.
I can't handle the stress no more, dog. These damn A levels.
So, all right, guys. Good luck, and I'll see you for physics if I'm not passed out.
I've had training.
The training is nothing. The will is everything. The will to act.
Yield.
You're still here?